What if everything we know about the universe, the stars, the galaxies, the very fabric of space and time, is just the tip of the iceberg? What if the reality we perceive with our senses is merely a thin veil draped over something far stranger, far more mysterious, and infinitely more complex? For centuries, humanity has peered up at the night sky, asking these very questions, driven by a curiosity that stretches beyond the visible, beyond the measurable, into the realms of the unimaginable. And yet, with every discovery, every leap in our understanding, we uncover not answers but deeper, more profound mysteries, each one hinting that our universe holds secrets we are only beginning to glimpse. Today, we're diving headfirst into that mystery, exploring 30 of the most astonishing theories about the universe's hidden realities, ideas that challenge everything we think we know. From dimensions folded within dimensions to parallel worlds brushing against our own, these concepts don't just expand our knowledge, they shatter our perception of what's possible. And while some may sound like science fiction, each is grounded in rigorous scientific inquiry, born from the minds of physicists, cosmologists, and visionaries who dare to ask, what if? This journey isn't just about theories, it's about reimagining reality itself and uncovering the breathtaking possibilities lurking just beyond the edges of our understanding. So, if you've ever looked up at the stars and wondered what lies beyond, if you've ever felt that tug of curiosity about the true nature of existence, then you're in the right place. This exploration is for the dreamers, the questioners, and the endlessly curious. Together, we'll venture into the unknown, examining ideas that range from the elegantly simple to the wildly speculative, each one offering a new lens through which to view the cosmos. By the end, you won't just have learned about these theories, you'll have felt the awe and wonder that comes with peering into the deepest mysteries of the universe. So let's begin. Our journey begins with perhaps the most mind-bending theory of all, one that forces us to question the very nature of our existence, the simulation hypothesis. This is the provocative idea that our universe, with all its vastness and complexity, is not a base reality but an incredibly sophisticated computer simulation, much like an ultra-advanced video game. The core of this argument was famously formalized by philosopher Nick Bostrom in 2003. He presented a compelling trilemma, a set of 3 possibilities, and argued that at least one must be true. The first option is that almost every civilization that reaches our level of technological maturity goes extinct before it can develop the capability to run such simulations. The second is that even if they do advance, they almost certainly choose not to run vast numbers of simulations of their ancestors. And the third, which is where things get fascinating, is that we are almost certainly living in a computer simulation right now. Bostrom's reasoning is statistical. If even one advanced civilization ever chooses to run countless ancestor simulations, the number of simulated minds would vastly outnumber the number of biological ones. Therefore, the odds that we are one of the rare original biological beings rather than one of the innumerable simulated ones are astronomically low. This isn't just a thought experiment confined to philosophy departments. Technologists like Elon Musk have pointed out the staggering rate of our own technological progress. From simple Pong just 50 years ago to photorealistic virtual realities and artificial intelligence today, the trajectory suggests that creating a fully immersive, indistinguishable simulation may be inevitable for a sufficiently advanced civilization. If that's the case, the question becomes not if such simulations are possible, but how we could ever know we aren't already inside one. The implications are profound, touching on everything from free will to the meaning of life. If our reality is programmed, are our choices our own, or are they predetermined lines of code? Is the pain we feel, the love we experience, any less real if it's simulated, or does the mere fact that we feel it grant it authenticity? Some scientists even speculate that potential glitches in the matrix, strange quantum behaviors, or unexplained cosmic constants could be evidence of the underlying code, like seeing the digital grid of a simulation through the veneer of our perceived reality. It's a theory that doesn't just place us in the universe, it places the universe inside something else entirely, redefining everything we thought we knew about what is real. But if the simulation hypothesis makes you question the foundation of your reality, the next theory expands the stage of existence to an almost incomprehensible scale. We are moving from the possibility that our universe is artificial to the staggering proposition that it is not even unique. This is the multiverse theory, the idea that our cosmos is just one of an infinite number of parallel universes, all existing simultaneously and comprising everything that ever could exist. This isn't a single idea but a framework that emerges from several distinct branches of physics, each pointing toward the same breathtaking conclusion. The first and perhaps most famous version comes from the strange world of quantum mechanics. In the quantum realm, particles don't have definite states until they are observed. They exist in a blur of probability called a superposition. The classic example is Schrödinger's cat, a thought experiment where a cat in a box is simultaneously alive and dead until someone looks inside. The many worlds interpretation, proposed by physicist Hugh Everett in 1957, offers a radical solution to this paradox. It suggests that at the moment of observation, the universe doesn't collapse into a single outcome. Instead, it splits into multiple branches. In one universe, you open the box and find a living cat relieved. In another, equally real universe, a different version of you finds a dead cat and is horrified. Every quantum event, every possible outcome creates a new branching timeline. This means there's a universe where you never clicked on this video and another where you are already watching part 3. Every decision, no matter how small, spawns new worlds. Another compelling strand of multiverse theory comes from cosmology and the theory of eternal inflation. Imagine the aftermath of the Big Bang not as a single expanding balloon, but as an endlessly bubbling foam. In this model, the energy driving the expansion of space is not evenly distributed. Most of space continues to inflate at a fantastic rate, but in certain pockets this inflation stops. Each of these pockets becomes a separate bubble universe with its own Big Bang and its own unique set of physical laws and constants. Our entire observable universe might be just one such bubble in an infinite cosmic foam. The laws of physics we take for granted, the strength of gravity, the mass of an electron, might not be fundamental truths but mere local bylaws, the random outcome of how our particular bubble formed. In another bubble, gravity could be repulsive, atoms might never coalesce, and life as we know it could be impossible. Or perhaps something even more incredible could have formed. This leads to the most profound implication of the multiverse, the idea of alternate realities that are not just different in their history, but in their very nature. With an infinite number of universes, every possible variation becomes not just likely, but inevitable. There is a universe where the Roman Empire never fell. A universe where you are a famous rock star, a universe made entirely of chocolate. While some of these might sound whimsical, the underlying principle is serious science. The fine-tuning of our universe's constants for life is one of cosmology's greatest mysteries. Why do the fundamental forces have exactly the strength required for stars to burn and atoms to bond? In a multiverse, there's no mystery. We simply live in one of the rare universes where the numbers came out right for us to exist and ask the question. We are the winners of a cosmic lottery, living in a universe that permits our existence, while an infinity of other, barren universes exist unnoticed. The majesty of this idea is that it doesn't diminish our universe, it makes our existence seem all the more precious and unlikely. We are not at the center of a single created cosmos, but rather a fascinatingly rare example of what can happen when the laws of physics align just so in a sea of infinite possibilities. Yet for all its mind-bending implications, the holographic principle didn't emerge from pure mathematical speculation. It was born from solving one of the most perplexing paradoxes in all of physics, centered on the most destructive objects in the cosmos, black holes. The story begins in the 1970s when a young physicist named Jacob Bekenstein made a startling proposition. He argued that a black hole must actually possess entropy, a measure of disorder or information. This was a radical notion because entropy is a property of systems with many constituent parts, like a gas made of molecules, while a black hole was thought to be fundamentally simple, defined only by its mass, spin, and charge. It seemed to erase all information about the star that formed it, violating a key tenet of quantum mechanics. That information cannot be destroyed. The great physicist Stephen Hawking initially opposed this idea, but his own work on quantum effects at the event horizon led him to a stunning conclusion. He found that black holes aren't completely black. They slowly radiate energy and evaporate over astronomical timescales. This raised a terrifying question. When a black hole evaporates completely, what happens to all the information about the matter that fell in? Is it truly lost forever? This black hole information paradox threatened to unravel the foundations of physics, pitting the smooth, deterministic laws of quantum mechanics against the warped, singular reality of general relativity. The holographic principle, largely developed by physicists like Leonard Susskind and Gerard T. Hooft, emerged as the most elegant solution. Their work suggested that all the information describing everything that falls into a black hole is not lost inside the singularity. Instead, it is perfectly encoded and preserved on the black hole's event horizon, the two-dimensional surface that marks the point of no return. Imagine writing an entire encyclopedia in a language of microscopic pixels on the surface of a sphere. The information isn't gone, it's just stored in a vastly different form, projected inward. This discovery revealed a profound universal law. The maximum amount of information that can be contained in any region of space is not proportional to its volume, as we would intuitively expect, but to the area of its boundary. A universe's information content is limited by its surface area, not its depth. This means the three-dimensional reality we experience, the feeling of solidity, the depth of space, the entire rich tapestry of the cosmos, could be a magnificent projection from a flat, two-dimensional surface at the very edge of the observable universe. Think of it like watching a high-definition movie on a screen. The image appears to have depth, with actors moving toward and away from you, but every bit of that information is stored on the flat, two-dimensional surface of the screen. Our universe could be a cosmic version of this, a breathtakingly complex and immersive projection. The laws of physics that govern our 3D world would then be akin to the rules of the projection, emergent properties of a deeper, simpler set of rules written on a distant 2D surface. This isn't to say our reality is an illusion in the sense of being fake. The emotions we feel and the stars we see are unquestionably real to us, but they might be real in the same way a character in a video game is real within its own world, a manifestation of underlying code operating on a simpler plane of existence. This principle turns our intuition inside out, suggesting that the truest description of reality might not be found in the world around us, but encoded on a distant, invisible wall we can never touch. But if the holographic principle challenges our perception of dimensions, our next theory confronts us with a fundamental void in our understanding of the cosmos itself. For nearly a century, astronomers have faced a persistent and unsettling problem. The universe simply doesn't add up. When we observe galaxies spinning like vast celestial pinwheels, the stars on the outer arms are moving so fast that the gravity from all the visible matter, the stars, gas, and dust, should be completely insufficient to hold them together. These galaxies should have torn themselves apart eons ago. The same gravitational math fails when we look at the movements of entire galaxy clusters. They are moving with a kinetic energy that the visible mass within them could never account for. There is only one conclusion. There must be something else there, a vast amount of something that exerts a powerful gravitational pull but emits no light and refuses to interact with ordinary matter in any other way. This invisible something is what we now call dark matter, and it is not a minor component. It makes up roughly 27% of the entire mass energy content of the universe, outnumbering the atoms that make up you, me, and every star we can see by a factor of more than 5 to 1. We are living in a universe dominated by a ghost, an entity we can only detect by the gravitational footprints it leaves behind. The primary strategy for hunting this ghost has focused on the idea that dark matter must be a particle, something left over from the fiery beginning of the universe. For decades, the leading candidate has been a class of particles known as WIMP, or weakly interacting massive particles. As the name implies, these hypothetical particles would have significant mass and interact with normal matter only through gravity and the weak nuclear force, the same force responsible for radioactive decay. This would make them incredibly difficult to detect, but not impossible. Deep underground, in mines and tunnels shielded from cosmic rays, extraordinarily sensitive experiments like LUX and Xenon have been waiting for the incredibly rare occasion when a WIMP might bump into the nucleus of an atom in a vat of ultra-pure liquid xenon. The quest has been immense, but so far these detectors have heard only silence. The predicted WIMP have stubbornly refused to appear, forcing physicists to broaden the search. This has led to increased interest in another theoretical particle called the action. Originally proposed to solve a different puzzle in particle physics, actions would be extremely light, billions of times less massive than an electron, and would behave more like a pervasive field than a discrete particle. If they exist, they could flood the universe, and their interaction with strong magnetic fields might cause them to convert into a faint microwave photon that we could potentially detect. Experiments like ADMS are using powerful, tuned magnets to act as cosmic radios, slowly scanning for the specific frequency that would signal the presence of this elusive particle. The search for a particle, whether WIMP or action, is a monumental effort to identify the missing 85% of the universe's matter. Yet, after decades of null results, some scientists have begun to question the entire premise. Could it be that we are not missing matter, but that we are misunderstanding gravity itself? This is the bold proposition of theories like MUND or modified Newtonian dynamics. Instead of invoking an invisible substance, MUND suggests that our equations for gravity, which work perfectly well on the scale of our solar system, simply break down at the immense scales of galaxies. It proposes a tiny modification to the force of gravity at extremely low accelerations, the kind experienced on the outer edges of a galaxy. With this one tweak, the rotation curves of galaxies snap into perfect agreement with observations without any need for dark matter. It's an elegant solution that does away with the need for a mysterious, undetectable substance. However, MUND faces its own significant challenges. While it beautifully explains the rotation of individual galaxies, it struggles to account for the observations of colliding galaxy clusters like the famous Bullet cluster. Here, the visible matter of two colliding clusters, the galaxies themselves, slams together and slows down, but the gravitational lensing effect shows that the majority of the mass has sailed right through the collision, completely separate from the galaxies. This is exactly what you would expect if the mass were made of collision-shy dark matter particles. But it is very difficult for modified gravity to explain how gravity could become separated from the visible mass that produces it. This compelling evidence has kept most cosmologists in the particle camp, but the mystery is far from settled. Whether particle or a flaw in our theories, the role of dark matter is absolutely critical to our existence. We can visualize it as the invisible scaffolding of the cosmos. In the early universe, slight overdensities in the dark matter distribution acted as gravitational seeds. Ordinary matter, attracted by this unseen pull, flowed into these wells, eventually becoming dense and hot enough to ignite into the first stars and form the galaxies we see today. Without dark matter's gravitational blueprint, the universe would be a vastly different place, a diffuse, dark, and structureless void. The fact that we live in a universe rich with galaxies, stars, and planets is a direct consequence of this dark, unseen architecture, a constant reminder that the most fundamental components of reality may still be hidden from our view. Just as dark matter's gravitational pull sculpts the universe on the largest scales, another, far more mysterious force is actively working against it, pushing the very fabric of spacetime apart. This is the enigma of dark energy, and its discovery was one of the most shocking and unexpected turns in the history of cosmology. For much of the 20th century, scientists were locked in a debate about the ultimate fate of the cosmos. Would the collective gravity of all the matter in the universe eventually slow its expansion, pulling everything back together in a cataclysmic big crunch? Or was there just barely enough energy for the universe to coast forever, expanding at a slower and slower rate, always approaching but never quite reaching a full stop? The answer, revealed in the late 1990s, was neither. Two independent teams of astronomers were studying distant supernova, specifically a type called Io supernova, which have a very predictable brightness. By measuring how much dimmer these standard candles appeared from Earth, they could precisely calculate how far away they were. By then comparing that distance to the redshift of their light, a measure of how much the universe has stretched since the star exploded, they could chart how the expansion rate of the universe has changed over billions of years. Everyone expected to find that the expansion was slowing down due to gravity's relentless pull. Instead, they found the exact opposite. The supernovae were fainter and therefore farther away than they should have been if the expansion were decelerating. The staggering conclusion was that the expansion of the universe is not slowing down at all, it is accelerating. Something is actively forcing galaxies to fly away from each other at an ever-increasing speed. This discovery was so profound it earned the teams the Nobel Prize in Physics in 2011, and it completely upended our understanding of cosmic evolution. So what is this repulsive force? We call it dark energy, but that's merely a name for our ignorance. It appears to be a property of space itself, a kind of anti-gravity that grows stronger as the universe expands and creates more space. It constitutes a staggering 68% of the total mass energy content of the universe, making it the dominant component of reality. The leading and most straightforward explanation comes directly from Einstein himself, though he initially considered it his greatest blunder. In his equations of general relativity, he included a term called the cosmological constant, represented by the Greek letter lambda. This was a repulsive force he mathematically added to balance the attractive force of gravity and achieve a static universe, which was the prevailing model at the time. After Hubble discovered the universe was actually expanding, Einstein discarded the idea. But with the discovery of the accelerating expansion, the cosmological constant was resurrected. In this modern view, empty space is not nothing. It seethes with a faint, intrinsic energy known as vacuum energy. According to quantum physics, virtual particles are constantly flickering in and out of existence in a vacuum, and this activity gives the vacuum itself an energy density. This vacuum energy would exert a negative pressure, causing spacetime to expand. The problem is one of scale. When physicists try to calculate the theoretical value of this vacuum energy, the number they get is off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. It is arguably the worst prediction in the entire history of science. This colossal mismatch between theory and observation is a clear sign that we are missing something fundamental. This has led to other, more dynamic explanations. One compelling alternative is a theory called quintessence. Named after the classical fifth element, quintessence proposes that dark energy is not a constant property of space but a dynamic energy field that permeates the entire cosmos. Unlike the cosmological constant, its strength could change over time. It could weaken, strengthen, or even change its character from repulsive to attractive. This opens up a much wider range of possible futures for the universe. Perhaps the acceleration is only a temporary phase. The ultimate fate of everything is tied directly to the true nature of dark energy. If it is indeed a constant cosmological constant, then the acceleration will continue forever. Billions of years from now, the expansion of space will become so rapid that galaxies outside our local group will be pushed away faster than the speed of light, vanishing forever from our observable universe. The sky will grow dark and empty, stars will burn out, and over incomprehensible timescales, even the protons that make up all matter may decay. The universe will approach a final state of maximum entropy, a vast, cold, and utterly dark emptiness where nothing ever happens again. This is the heat death of the cosmos, a silent and lonely end. However, if dark energy is something like quintessence that could grow stronger, a far more dramatic finale awaits. In a scenario known as the Big Rip, the accelerating expansion could eventually overcome all forces, not just gravity. First, galaxy clusters would be torn apart, then individual galaxies. In the final moments, the repulsive force would rip apart stars, planets, and even atoms and atomic nuclei themselves, shredding the very fabric of spacetime. The accelerating expansion, driven by this unseen and enigmatic force, doesn't just dictate the future. It forces us to confront the humbling reality that the universe is dominated by entities we cannot see and forces we do not yet understand. Yet for all its power, dark energy is not the only force hinting at a deeper layer of reality. To truly understand the universe's fundamental ingredients, we must venture down to the smallest possible scales, where our conventional ideas of particles and forces break down entirely. This brings us to one of the most ambitious and mathematically beautiful frameworks ever devised, string theory. At its heart, string theory proposes a radically simple answer to an ancient question. What is the universe ultimately made of? For decades, the standard model of particle physics has described a zoo of fundamental particles, electrons, quarks, photons, as point-like, zero-dimensional objects. They are the dots in the cosmic connect the dots picture, but this picture runs into insurmountable problems when we try to include gravity, creating mathematical infinities that simply don't make sense. String theory offers an elegant solution. It suggests that at the very tiniest scale, the Planck length, these particles are not dots at all. Instead, they are incredibly tiny, vibrating loops or strands of energy strings. Imagine a minuscule, oscillating rubber band. Just as a single violin string can vibrate at different frequencies to produce distinct musical notes, a middle C, a G sharp, a fundamental string can vibrate in different patterns. One specific resonance might give rise to the properties of an electron, its specific mass and negative charge. A different, higher energy vibration might manifest as a photon, the particle of light. Another could create a quark. In this stunning vision, every particle in the universe, every building block of matter, and every force carrier is just a different note on the same cosmic instrument. The universe is not a collection of things, but a symphony of vibrations. This beautiful idea, however, comes with an extraordinary requirement. For the mathematics of these vibrating strings to work consistently, to avoid those dreaded infinities and include gravity, they cannot do their dance in the three spatial dimensions we know. The equations of string theory only hold together in a universe with 10 or even 11 spatial dimensions. This immediately raises an obvious and pressing question. If there are all these extra dimensions, where are they? Why do we only experience 3 of space and 1 of time? The leading answer is a process called compactification. theorists propose that these extra dimensions are not vast and expansive like the ones we know. Instead, they are curled up or folded in upon themselves at every single point in space into an unimaginably tiny, complex shape. To grasp this, think of a common everyday object, a garden hose. From a great distance, the hose looks like a simple one-dimensional line. But if you were an ant crawling on its surface, you would discover a second dimension curled around the hose's circumference. In the same way, at every point in our familiar three-dimensional space, there could be 6 or 7 additional dimensions curled up into a fantastically small, intricate geometric shape known as a Calabi-Yau manifold. These shapes are not random. Their specific geometry determines the resonant patterns of the strings vibrating within them, which in turn dictates the laws of physics we observe, the masses of particles, the strength of forces, and the number of dimensions that appear large to us. Our entire universe, with its specific physical constants, might just be the unique outcome of how our particular Calabi-Yau manifold is folded. This is where string theory's grand promise lies: unification. For centuries, physics has sought a single, overarching principle that can explain all forces. We have two brilliantly successful but utterly incompatible theories: general relativity, which governs the immense gravity of planets and galaxies, and quantum mechanics, which rules the chaotic world of the atom. One describes the bending of spacetime, the other describes probability and uncertainty. They have never been reconciled. String theory aims to be that theory of everything. Because the graviton, the hypothetical particle that carries the gravitational force, naturally emerges in the theory as a specific vibration of a closed string, gravity is not added as an afterthought. It is woven into the fabric of the theory from the very beginning. In this framework, the 4 fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, are all just different manifestations of strings interacting in a higher dimensional reality. Despite its profound mathematical elegance and promise, string theory remains just that, a theory. It has yet to make a single testable prediction that can be verified by experiment. The energy levels required to see strings directly or to probe these compactified dimensions are far beyond the reach of any particle accelerator we could ever hope to build. This has led some critics to question whether it is even a scientific pursuit. Yet for its proponents, the mathematical consistency and its innate ability to include gravity are clues so powerful they suggest we are on the right track, even if the final proof remains hidden in dimensions we cannot perceive. It represents a monumental leap of imagination, proposing that the true nature of reality is not found in particles, but in music, and that the cosmos is built not of stuff, but of beautiful, vibrating strings playing the score of existence in a hidden, multidimensional space. But if string theory reimagines the building blocks of reality, our next theory forces us to question one of the most fundamental aspects of our everyday experience: the nature of time itself. We all feel time's relentless, one-way march. We remember the past, we experience the present, and we anticipate the future. This seems so obvious it's almost beyond question. But what if this flow, this arrow of time, is the ultimate illusion? What if the past, present, and future are not sequential but exist simultaneously in a single, frozen structure? This is the startling implication of the block universe theory, a view of reality that emerges directly from Einstein's theory of relativity. The block universe model proposes that time is a dimension, much like the 3 dimensions of space. We are comfortable thinking of space as a container. An object exists at a certain latitude, longitude, and altitude. In the block universe, an event exists at a certain latitude, longitude, altitude, and moment in time. From this 4-dimensional perspective, the entire history of the universe, from the Big Bang to the farthest possible future, is laid out eternally. Your birth, your life, and everything that will ever happen to you are all fixed points in this vast 4-dimensional block. There is no special now that moves. The feeling of a moving present is just a feature of our consciousness, a way our brains process this static reality. The physicist Brian Greene often uses a simple analogy. Think of a film strip. The entire movie exists all at once on the reel. When we play it, we experience one frame after another, creating the illusion of motion and change. But the frames themselves are permanent and unchanging. In the block universe, we are not the audience watching the film. We are the characters inside the film, and the entire reel already exists. This idea is not just philosophical speculation. It is a direct consequence of Einstein's work. His theory of special relativity shattered the notion of absolute simultaneity. It showed that two events that appear to happen at the same time for one observer can happen at different times for another observer moving at a different speed. Your now is not the same as everyone else's now. There is no universal clock ticking away for the entire cosmos. This means the concept of a single, universal present moment that sweeps across the universe is fundamentally flawed. Instead, reality is better described as a network of events, each connected to others in a rigid four-dimensional structure called space-time. In this structure, the distinction between past, present, and future is a matter of perspective, not an objective feature of the universe. This presents a profound paradox between physics and psychology. Physically, the universe might be a static block, but psychologically, we experience a relentless and irreversible flow. Why does time feel like it moves forward? The answer likely lies not in the fundamental laws of physics, but in the concept of entropy from thermodynamics. Entropy is a measure of disorder, and the second law of thermodynamics states that in a closed system, entropy always increases over time. Think of an ice cube melting in a glass of water. It moves from a state of low entropy, a structured, ordered ice cube, to high entropy, a disordered puddle of water. This process is irreversible. You never see a puddle spontaneously form an ice cube. Our brains are incredible entropy detection machines, and we are constantly observing the universe moving from order to disorder. We remember the past because it was a state of lower entropy, and we anticipate the future as a state of higher entropy. This psychological arrow of time, defined by the increase of disorder, is what creates our powerful, inescapable sensation that time is flowing in one direction. It is the story our minds tell us as we navigate the frozen landscape of the block universe. The implications of this are both liberating and deeply unsettling. It challenges our deepest intuitions about free will and destiny. If the future is already out there, just as real as the past, are our choices truly free? Philosophers and physicists debate this fiercely. Some argue that the block universe is deterministic, that every event is preset. Others suggest that the block contains all possible outcomes, and our experience of making a choice is what selects one path through the many that are available. What remains clear is that our everyday perception of time is a useful, powerful, but ultimately limited view of a much stranger and more magnificent reality. We are time travelers in a sense, but not by moving through time, by having our consciousness focused on one moment at a time, illuminating a single slice of the infinite block that is our existence. If the block universe suggests our experience of time is an illusion, then the next theory on our journey challenges the very nature of our existence in a way that is almost too strange to comprehend. It asks a deeply unsettling question. If the universe is vast and old enough, could a single, conscious brain simply pop into existence, complete with all its memories and senses, out of nothing more than random chance? This is the thought experiment known as the Boltzmann brain, named for the 19th century physicist Ludwig Boltzmann, who helped lay the foundations for our modern understanding of thermodynamics and entropy. To understand how such an absurd idea could even be proposed, we need to revisit the second law of thermodynamics and the concept of entropy. The law states that the entropy of a closed system always increases over time. Things move from order to disorder. A shattered glass does not reassemble itself, but the law is statistical, not absolute. It is not physically impossible for all the air molecules in a room to suddenly rush into one corner. It is just so astronomically unlikely that it will never happen in the lifetime of the universe. However, if you wait long enough, really, truly long enough, over timescales that make the current age of the universe seem like a single blink, these incredibly rare fluctuations become not just possible but inevitable. In a universe that persists for a near eternity, even the most improbable events are destined to occur. Now, apply this to the far, far future. If the prevailing theory of dark energy is correct and the cosmos is headed for a heat death, a vast, cold, empty void where the temperature uniformly approaches absolute zero, then the universe will eventually reach a state of maximum entropy. It will be a featureless sea of equilibrium, but even in this final state, tiny, random fluctuations in energy would still occur due to quantum mechanics. Over incomprehensible eons, one of these fluctuations could, by sheer accident, be significant enough to assemble a fully formed, conscious human brain, complete with a lifetime of false memories. This brain would flicker into existence for just a moment, believing itself to be a person living in a world, before the overwhelming entropy of the void instantly dissolved it back into nothingness. This is the Boltzmann brain, a disembodied consciousness that hallucinates an entire reality, only to cease existing a fraction of a second later. So why is this bizarre idea more than just a philosophical curiosity? It poses a massive problem for modern cosmology. The theory of cosmic inflation, which explains the initial conditions of our universe, suggests that our observed cosmos, with its incredibly low entropy at the Big Bang, is itself the result of a rare statistical fluctuation. In an eternally existing multiverse or a universe headed for heat death, the vast majority of all conscious experiences would not be like ours, sustained over decades within a structured universe. Instead, they would be the fleeting, isolated experiences of Boltzmann brains forming in the void. There would be infinitely more of these disembodied minds than there are minds like ours embedded in a real, ordered cosmos. Therefore, if our current cosmological models are correct, the odds are overwhelmingly greater that you and I are not real people in a real universe, but are instead Boltzmann brains momentarily hallucinating our entire existence. This is a logical conclusion that most physicists find profoundly unsatisfying, as it essentially invalidates all of science. If we can't trust that our memories and observations of an ordered past are real, then we can't trust any scientific inference. This paradox forces cosmologists to carefully refine their models. A viable theory of the universe's origins must make the formation of a stable, low-entropy universe like ours much more probable than the formation of a lone Boltzmann brain. Some solutions involve the nature of dark energy. If dark energy is not a true cosmological constant but instead decays over time, it could prevent the universe from reaching a true maximum entropy state, thereby shutting off the possibility for these fluctuations. The Boltzmann brain problem acts as a crucial sanity check, a tool for testing which cosmological models are truly plausible. It is deeply intertwined with the anthropic principle, the idea that the universe must be compatible with the conscious life that observes it. In this case, the principle suggests that we must live in a cosmos where the conditions make sustained, ordered observers like us vastly more likely than fleeting, disordered ones. We don't just observe the universe. Our very existence as stable observers tells us something fundamental about its ultimate fate. But if the Boltzmann brain makes our place in the cosmos feel fragile and possibly illusory, the next theory offers a perspective that is both ancient and radically modern, placing consciousness itself at the very heart of existence. We are venturing into the realm of cosmic consciousness, a set of ideas proposing that mind is not a late arriving product of the universe, but its fundamental foundation. This flips the standard scientific story on its head. The conventional view, known as emergentism, is that consciousness is an emergent property of complex computation in biological brains. As neurons connect and fire in intricate networks, the property of subjective experience, the feeling of what it's like to be you, somehow arises from the machinery. It's a compelling idea, but it leads to the so-called hard problem of consciousness, famously articulated by philosopher David Chalmers. We can understand how the brain processes colors, but we cannot explain how and why those electrochemical signals generate the actual inner experience of the color red. How does objective matter produce subjective mind? One compelling alternative is panpsychism, the view that consciousness is a universal and fundamental feature of all matter. The word itself comes from the Greek pan, meaning all, and psyche, meaning soul or mind. In this view, consciousness did not emerge at some point in evolutionary history. Instead, it was always there, a basic property of the universe like mass or charge. This doesn't mean that a rock is contemplative or an electron is sad. That commits the fallacy of composition, assuming the parts have the same properties as the whole. Instead, panpsychists suggest that even the most elementary particles possess an extremely simple, prototypical form of experience, perhaps just a vague, raw awareness. When these particles combine into incredibly complex systems, like a human brain, these tiny bits of proto-consciousness combine to form the rich, complex tapestry of our own subjective inner world. Your mind is not a ghost in the machine. It is the complex symphony of billions of tiny mental notes played by the fundamental constituents of your brain. This elegantly solves the hard problem by stating that consciousness was never generated. It was simply organized. This idea finds a strange and controversial partner in the quantum realm, leading to the quantum consciousness hypothesis. Some physicists like Roger Penrose and anesthesiologist Stuart Hameroff propose that the bizarre, fuzzy nature of quantum mechanics is not just involved in consciousness but is its very engine. Their theory, called orchestrated objective reduction, suggests that within the neurons of our brains, specifically in structures called microtubules, quantum superpositions occur. These are states where particles exist in multiple possibilities simultaneously. According to their model, consciousness is the process of these quantum superpositions collapsing into a single definite state. Each collapse is a moment of experience, a discrete event in the stream of awareness. This would directly tie our inner world to the most fundamental level of physics, suggesting that we are not just observers of the quantum world but active participants whose observation literally brings reality into focus. This leads us to the most famous and debated intersection of consciousness and physics, the observer effect in quantum mechanics. In the classic double-slit experiment, when we fire particles like electrons at a barrier with two slits, they behave like waves, creating an interference pattern on the back screen. But the moment we place a detector to see which slit each electron goes through, the wave-like behavior vanishes and the electrons behave like simple particles. The act of observation, of measurement, seems to force the quantum system to choose a definite state. The orthodox Copenhagen interpretation of quantum mechanics states that a particle does not have definite properties until it is measured. This has led to profound and often misinterpreted philosophical claims that consciousness itself causes the wave function to collapse. The implication is staggering. Reality remains in a blurred state of potentiality until a conscious mind observes it, effectively bringing the concrete world into existence. Most physicists are quick to point out that observation in this context does not require a human consciousness. It simply means a physical interaction with any measuring device. A Geiger counter is an observer, a photographic plate is an observer, yet the nagging question remains: what ultimately constitutes an observation that completes the chain? If a device causes the collapse, what observes the device? This chain seems to lead back to a conscious perceiver. suggesting that mind and world are not separate but deeply entangled. The universe may not be a cold, clockwork mechanism but a participatory reality, one that requires consciousness to actualize its potential. This perspective is beautifully illustrated by the structures of the cosmos itself. When we look at the large-scale distribution of galaxies, we see a vast cosmic web, a network of filaments and nodes that looks uncannily like the neural network of a human brain. This is more than just a poetic coincidence. The underlying physics of how gravity structures matter and how electrical signals structure thoughts may follow similar mathematical patterns of network optimization. It presents a breathtakingly holistic vision. The universe is not a place that contains conscious beings. It is a conscious being waking up to itself, one observer at a time, from the smallest particle to the grandest galaxy. Yet if the nature of consciousness challenges our understanding of reality from within, the next theory does so by looking to the extremes of cosmic structure, to objects so bizarre they seem to rewrite the rules of physics entirely. We arrive now at one of the most fascinating and paradoxical ideas in all of theoretical cosmology, the concept of white holes. By now, everyone is familiar with the terrifying majesty of a black hole, a region of space-time where gravity is so intense that nothing, not even light, can escape its pull once it crosses the event horizon. But what if we could run the film of a black hole in reverse? What would that look like? This is precisely what a white hole is theorized to be. It would be a region of space-time from which nothing can enter. Instead of irresistibly pulling everything in, a white hole would violently expel matter and energy outward, like a cosmic fountain endlessly erupting from a singular point. It is the mathematical opposite of a black hole, and its existence is written directly into the equations of Einstein's general theory of relativity. Every solution that describes a black hole also, mathematically, describes a white hole. They are two sides of the same coin. The thermodynamic objections to white holes are immediate and powerful. They appear to be machines that create energy from nothing, spewing out matter and radiation without any apparent source, which would blatantly violate the sacred second law of thermodynamics. A universe that allowed white holes would be a universe where entropy could spontaneously decrease, where shattered glasses could reassemble themselves. For this reason, most physicists have long considered them to be mathematical curiosities without any basis in physical reality. However, new and daring cosmological models are beginning to suggest that white holes might not be impossible after all. They might simply be hidden from our view in a surprising way. One compelling idea is that what we perceive as the birth of our entire universe, the Big Bang itself, could be viewed as the ultimate white hole event, a singular, explosive eruption of all matter, energy, and space-time from a point of infinite density. In this view, the entire cosmos is not falling into a black hole, but is instead being ejected from a white hole. The connection goes even deeper when we consider the fate of black holes. Stephen Hawking's groundbreaking work showed that black holes are not entirely black. They slowly evaporate over astronomical timescales by emitting a faint glow of radiation. But what happens at the very end of this evaporation, when the black hole has shrunk to a microscopic size? The equations of general relativity break down, creating a singularity, a point of infinite density where our understanding of physics ceases to work. Some quantum gravity theorists like Carlo Rovelli propose a breathtaking resolution to this problem. The tiny, ancient black hole doesn't just vanish. Instead, it undergoes a quantum bounce, transforming into a white hole. In this model, the matter that fell into the black hole eons ago isn't lost forever. It is trapped, compressed, and eventually reborn, ejected back into the universe in a blinding flash after a timescale that is unimaginably long but finite. This process would preserve information and avoid the dreaded singularity, offering an elegant solution to the black hole information paradox. This leads to a fascinating question. If white holes can form from dying black holes, why have we never seen one? The answer may lie in the extreme time dilation predicted by relativity. From the perspective of an outside observer watching a black hole form and then evaporate, the transformation into a white hole would occur on a timescale of billions upon billions of years. We are living in a universe that is far too young for any of the black holes formed from dead stars to have reached this final stage of their life cycle. However, there is a tantalizing possibility. If a primordial black hole was created in the violent energy of the Big Bang itself and was very small to begin with, it could be completing its evaporation and quantum bounce into a white hole right now in our modern epoch. Such an event would appear to us as a tremendous, inexplicable cosmic explosion. Astronomers have catalogued incredibly powerful events like gamma-ray bursts and fast radio bursts whose origins are not fully understood. Could some of these be the signature of a white hole, a cosmic rebirth happening in the depths of space? While still highly speculative, the idea provides a thrilling link between the most extreme objects in the universe and the fundamental laws that govern reality itself, suggesting that even death by black hole may not be the end, but merely a transition into a new and explosive form of existence. While the idea of a white hole rebirth offers a cosmic perspective on existence, our next theory brings the question of survival shockingly close to home, diving into one of the most personal and unsettling thought experiments in modern physics, quantum immortality. This concept pushes the many worlds interpretation of quantum mechanics to its absolute logical extreme, proposing a startling conclusion about the nature of consciousness and death. It all centers on a grim but fascinating thought experiment known as quantum suicide. Imagine a willing participant sits in front of a specially designed apparatus. This device is linked to a mechanism that measures the quantum state of a single particle, something like the spin of an electron, which is in a superposition of both up and down until the moment it is observed. The apparatus is rigged so that if the measurement results in spin up, a gun fires and kills the participant instantly. If the measurement results in spin down, nothing happens and the participant hears only an empty click. According to the standard Copenhagen interpretation, each time the experiment is run, there is a 50% chance the participant dies, but the many worlds interpretation tells a very different story. It says that at the moment of measurement, the universe splits into two equally real branches. In one universe, the spin is measured as up and the participant dies. In the other universe, the spin is measured as down and the participant lives. Now, the experiment is repeated again and again. From the perspective of an outside observer in any one branch, the participant will almost certainly be dead after just a few iterations. The odds of survival plummet with each click of the device, but from the perspective of the participant's own conscious experience, something bizarre happens. In the branching universe where the gun fires, that version of the participant's consciousness ceases. However, in the branch where the gun does not fire, the participant remains fully aware. And when the experiment is repeated, that conscious self will only ever experience the outcome where they survive. They will hear click after click after click, surviving against all astronomical odds, forever wondering why the gun never seems to fire. Their conscious experience is never terminated. It simply continues along the single timeline in the vast multiverse where every quantum fluctuation just happens to go their way. This leads to the disturbing core of quantum immortality. The idea that your subjective consciousness might be incapable of experiencing its own cessation. You cannot observe your own death because the moment of death is the end of observation. Therefore, from your first-person point of view, you might be forced to always find yourself in a reality where you continue to exist, no matter how unlikely that survival may be. This isn't about being invincible. You could still be horribly injured in countless branches. but the version of you that retains a continuous stream of consciousness will always be the one that, through sheer chance, avoids fatal injury. You would become a spectator to your own incredible luck, living through car crashes, natural disasters, and diseases, always surviving due to a bizarre sequence of quantum events. The philosophical implications for personal identity are profound and deeply unsettling. This theory challenges the very notion of a single, continuous self. Are you the same person from one moment to the next, or are you a constantly shifting point of awareness, hopping between branches in the multiverse, forever discarding the versions of yourself that perish? It suggests that identity is not a fixed thing but a path, a specific thread of experience winding its way through an infinite tapestry of possibilities. This also raises a thorny existential question. If this theory were true, why do we see people around us die? The answer is that from our external perspective, we are witnessing the endpoints of other branching timelines. We see the versions of people whose conscious experience in our particular branch has ended, but from their own subjective perspective in another branch, their consciousness continues uninterrupted. Everyone might be, from their own point of view, functionally immortal, living in a reality uniquely tailored to their continued existence, while we only witness their mortal counterparts in our own world. It is crucial to understand that quantum immortality remains a highly speculative fringe idea, a thought experiment that explores the boundaries of interpretation rather than a practical reality. Most physicists dismiss it as a misinterpretation of the many worlds theory or a logical paradox that highlights the flaws in taking an interpretation too literally. The theory faces enormous practical obstacles. For one, death is rarely a truly quantum event. It is usually the macroscopic, classical outcome of a vast number of particles. Aligning all the necessary quantum events to consistently avoid death in at least one branch becomes exponentially improbable. Furthermore, the theory offers no comfort, as the continuing consciousness would likely find itself in a reality of ever-increasing isolation and suffering, surviving catastrophes that leave it utterly alone. Ultimately, quantum immortality stands as a stark reminder of the strange and counterintuitive places that quantum theory can lead us, forcing us to confront the deepest questions about what it means to be a conscious self in a reality that might be infinitely branching. But if quantum immortality offers a bizarre form of personal survival, our next theory presents a threat so absolute and all-encompassing that it would erase not just life, but the very laws of physics themselves. This is the concept of false vacuum decay, and it is arguably the most existential and terrifying doom scenario in all of cosmology. To understand it, we need to revisit the idea of fields. In modern physics, the universe isn't mostly empty space. It's filled with invisible energy fields. The most famous of these is the Higgs field, which is what gives fundamental particles their mass. Think of these fields like a landscape. Most fields exist in their lowest possible energy state, a stable valley where they naturally settle. This is called a true vacuum. But what if our universe's Higgs field isn't in the true vacuum valley? What if it's perched on a higher energy hill in what physicists call a metastable or false vacuum state? It's stable for now, like a ball sitting perfectly balanced on the top of a hill. It can sit there for a very, very long time, but if it gets just a tiny nudge, a sufficient quantum fluctuation, it could suddenly roll down into a much deeper, lower energy valley, the true vacuum. This shift wouldn't just change the field, it would rewrite the rules of reality. The calculations surrounding the stability of the Higgs field are complex and depend on the precise mass of the top quark and the mass of the Higgs boson itself. For years, the results have been unsettlingly ambiguous. The best estimates suggest our universe might indeed be in this precarious metastable state. The energy difference between our false vacuum and the true vacuum would be colossal. If such an event were triggered somewhere in the universe, a bubble of true vacuum would spontaneously form and begin expanding in all directions at the speed of light. The laws of physics inside this bubble would be completely different. The fundamental constants we rely on, the strength of forces, the masses of particles, would change instantly. Atoms could no longer hold together. The very fabric of matter would disintegrate. This wave of destruction would be utterly undetectable until it arrived. There would be no warning, no flash of light, no time to react. One moment, the universe would be operating under the familiar laws of physics. The next moment, as the bubble wall passed through, everything would simply cease to exist in any recognizable form. Life, planets, stars, and galaxies would be erased, replaced by a new, alien reality governed by different, and almost certainly inhospitable physical laws. What makes this scenario so chilling is its inevitability and its stealth. If our universe is in a false vacuum, the decay is not a matter of if but when. The odds of it happening in any given cubic meter of space per year are astronomically low. But across the entire observable universe over billions of years, the probability rises. It could happen 5 seconds from now, or it might not happen for trillions of years. There is no way to predict it, and because the wall of the bubble expands at light speed, the event horizon of our doom would be the same as our event horizon for information. We couldn't see it coming. The first and only sign would be the instantaneous and complete transformation of reality itself, a silent, light-speed apocalypse that rewrites the cosmos. Yet, even as we confront the terrifying possibility of a cosmic reset from within, another theory offers a breathtakingly expansive vision of creation, suggesting our universe is not a solitary entity but merely one bubble in an infinite and ever-growing cosmic foam. This is the theory of eternal inflation, and it provides one of the most compelling frameworks for a true multiverse. To understand it, we need to rewind to the very beginning, to a fraction of a second after the Big Bang. The prevailing theory of cosmic inflation proposes that the newborn universe underwent an unimaginably rapid exponential expansion, doubling in size perhaps 100 times or more in less than a blink of an eye. This explosive growth smoothed out the cosmos, explaining why the universe appears so uniform in every direction we look. But what if this inflationary period didn't have a clean, universal end? What if, in most of space, it never stopped? This is the core of eternal inflation. Imagine the fabric of spacetime is not a single entity but a vast, bubbling cauldron of energy, often called the inflaton field. In most regions, this field remains in a high-energy state, causing space to inflate at a fantastic rate. This rapid expansion is so violent that it quickly outpaces the speed of light, constantly creating new volume. But quantum mechanics tells us that no field is perfectly stable. It is subject to tiny, random fluctuations. In some of these rapidly inflating regions, a quantum fluctuation will cause the inflaton field to randomly drop into a lower energy state. When this happens, the tremendous energy that was driving the inflation must be released. This colossal release of energy is what we call a Big Bang. It heats the region, fills it with particles, and allows it to evolve into a stable, slowly expanding universe like our own. Each of these drops creates a separate bubble universe, forever isolated from the others by the ever-inflating space that continues to expand between them at speeds we can never hope to cross. Within this magnificent and dizzying framework, our entire observable cosmos, with its hundreds of billions of galaxies, is just one such bubble, but we are not alone. The underlying inflationary background is eternal, constantly churning out new bubble universes. Each one forms with its own unique set of physical laws and constants, determined randomly by the specific way its local inflaton field settled. In this scenario, the fundamental forces we take for granted are not universal truths. They are merely the local bylaws of our particular bubble. The strength of gravity, the mass of the electron, the strength of the nuclear forces. these values were not designed, they were randomly selected when our bubble nucleated. In another bubble, gravity might be so strong that stars form, burn, and collapse into black holes in mere moments. In another, the weak nuclear force might be too weak to allow for the nuclear fusion that powers stars, leaving the universe dark and lifeless. The possibilities are as endless as the inflating void itself. This provides a powerful and elegant solution to one of cosmology's greatest mysteries, the problem of fine-tuning. Why do the constants of nature seem so exquisitely calibrated to allow for the existence of life? If the strength of the strong nuclear force were just a few percent different, carbon atoms could never form in the hearts of stars, making our chemistry and us impossible. If the cosmological constant were slightly larger, the universe would have ripped itself apart before galaxies could ever form. From the perspective of a single universe, this incredible precision seems to demand an explanation, perhaps a designer. But in the context of eternal inflation, no explanation is needed. With an infinite number of bubble universes, every possible combination of physical constants will be realized an infinite number of times. We do not live in a universe that is magically fine-tuned for life. We simply live in one of the rare bubbles where the random dice roll happen to produce constants that allow for stars, planets, and conscious beings to arise. We are the inevitable result of a statistical probability played out across an infinite canvas. We are not special, we are just lucky, living in a hospitable neighborhood in a multiverse filled with mostly barren and hostile realities. This perspective doesn't diminish our universe, it makes our existence within it a fascinating and precious accident, one story in an infinite library of cosmic possibilities. This radical perspective takes the awe we feel for black holes and turns it inward, suggesting that we might not just be looking at these cosmic monsters, but actually living inside one. Black hole cosmology proposes that our entire universe, from the Big Bang to the farthest galaxy, exists within the event horizon of a four-dimensional black hole residing in a larger parent universe. At first glance, this seems like pure science fiction, but it emerges from a fascinating convergence of mathematics and cosmology. The equations that describe the collapse of a star into a black hole and the equations that describe the expansion of our universe from a hot, dense state are strikingly similar. Both involve a singularity, a point of infinite density where the known laws of physics break down. For a black hole, the singularity lies in its future, the final destination for anything that falls in. For our universe, the singularity lies in our past, the Big Bang. Black hole cosmology simply asks, what if they are the same thing? What if the Big Bang was not the absolute beginning of everything, but the moment a shell of matter collapsed into a black hole in another universe, creating a new, self-contained spacetime within? This idea provides an elegant, though mind-bending, explanation for the initial conditions of our cosmos. One of the great mysteries of the Big Bang is why the early universe was in such a state of incredibly low entropy, a condition of exquisite order that allowed for the formation of complex structures. If our universe was born from a black hole, this low entropy state has a ready-made explanation. A black hole is ironically the object with the highest possible entropy in our universe. It represents maximum disorder. But from the perspective of the universe outside, the material that formed the black hole was highly ordered. When that ordered material collapsed, it could have created a new region of space-time, our universe, with that initial low entropy inheritance. Furthermore, the incredible, rapid expansion we call cosmic inflation could be understood as the violent birth pangs of this new spacetime realm, the explosive rebound of matter and energy at the moment of its creation within the black hole. This theory also offers a profound new perspective on the fate of information. The black hole information paradox asks what happens to all the information about the matter that falls into a black hole. If our universe is inside a black hole, the answer becomes beautifully recursive. the information isn't lost. Instead, it is translated, imprinted onto the two-dimensional surface of the event horizon that defines the boundary of our cosmos, and then projected inward to create the three-dimensional reality we experience, much like the holographic principle suggests. We are not the victims of information loss. We are the living embodiment of it, a universe built from the transformed information of a star that died in a higher dimensional reality. Perhaps the most staggering implication of this model is that it naturally creates a multiverse, but not one of parallel timelines. It suggests a cosmic matryoshka doll of nested universes. Every black hole that forms in our universe could, in turn, contain an entire new cosmos within it, with its own physical laws spawned from the specific conditions of its parent's collapse. Our universe could be just one generation in an infinite lineage of cosmic births, and this leads to a haunting question about our own black holes. When a star collapses in our night sky, forming a new black hole, are we witnessing the birth of a new universe completely separate and isolated from our own? Are we, in a sense, cosmic parents, unknowingly creating entire realms of existence with every stellar death? This vision of reality is both humbling and magnificent, placing us not at the center of a single creation, but as a fleeting moment in an infinite cycle of universes being born within universes, forever hidden from each other by the ultimate veil, the event horizon of a black hole. If black hole cosmology suggests our universe might be hidden behind an event horizon, our next theory offers a potential escape route, or at least a cosmic shortcut. Imagine folding a piece of paper so that two distant points touch. A wormhole is the universe's version of that fold, a tunnel through the hyperdimensional substrate of space-time itself that could connect two incredibly distant locations or even two different moments in time. The concept has its roots in a classic solution to Einstein's equations of general relativity, discovered by Albert Einstein and Nathan Rosen in 1935. They found that the equations describing a simple, non-rotating black hole, a Schwarzschild black hole, could be extended to reveal not a point of infinite density, but a bridge to another region of spacetime. This structure became known as an Einstein-Rosen bridge. For a while, this was seen as little more than a mathematical curiosity because these original bridges were completely impractical. They were incredibly unstable, pinching off into a singularity before any object or even a ray of light could possibly traverse them. They were less a tunnel and more a cosmic dead end. The modern concept of a potentially usable wormhole emerged from the work of physicists like John Wheeler, who coined the term, and later Kip Thorne, who took the idea and ran with it in the 1980s. Thorne was exploring the possibility of whether these structures could be made stable and traversable. The key, he realized, was a substance with truly bizarre properties, exotic matter. This isn't just matter that's weird or unknown. It's matter that possesses negative energy density or negative pressure. According to general relativity, the enormous gravitational pull trying to crush a wormhole shut could be counteracted and held open by this exotic matter lining the throat of the tunnel. It would act as a kind of anti-gravity scaffolding, propping the gateway open and making travel through it a theoretical possibility. The search for such matter isn't entirely science fiction. Weird quantum effects like the Casimir effect demonstrate that negative energy densities can exist in laboratory settings on a tiny scale. The monumental challenge, of course, would be producing and harnessing enough of this exotic material to stabilize a wormhole large enough to traverse. This leads to one of the most thrilling applications of wormhole theory, time travel. Because general relativity treats space and time as a single fabric, a wormhole could connect 2 points not just in space but in time. Imagine one mouth of a wormhole is placed on a spaceship that accelerates to near the speed of light. Due to time dilation from special relativity, time would pass much more slowly for the moving mouth compared to the stationary one left on Earth. If the spaceship returns after what its crew experiences as a few years, decades might have passed on Earth, the wormhole would now connect those two different moments in time. Walking through it from the ship's mouth would send you back to the era when the ship departed, while stepping through from Earth would catapult you into the future relative to the ship. This creates a closed time-like curve, a path through spacetime that loops back on itself, allowing for travel into the past. However, this immediately raises the specter of famous paradoxes, like the grandfather paradox, where you could go back in time and prevent your own grandfather from meeting your grandmother, thereby preventing your own existence. Physicists speculate that the laws of quantum mechanics might somehow prevent such logical inconsistencies, perhaps through a mechanism that only allows self-consistent events to occur. But this remains one of the deepest and most contentious puzzles in theoretical physics. Perhaps the most profound modern development in wormhole physics is their unexpected and deep connection to quantum entanglement, the phenomenon Einstein famously called spooky action at a distance. When two particles become entangled, they share a single quantum state. Measuring the property of one particle instantly determines the property of the other, no matter how far apart they are. This seems to violate the cosmic speed limit set by the speed of light, but it doesn't allow for the transmission of information. In recent years, physicists like Juan Maldaisner and Leonard Susskind have proposed a revolutionary idea called the ER=EPR conjecture. This suggests that the mysterious connection of quantum entanglement might be physically manifested in the fabric of space-time as a microscopic wormhole. In this view, two entangled particles aren't communicating faster than light. They are essentially connected by a minuscule Einstein-Rosen bridge. This provides a geometric picture for quantum non-locality, weaving together the two great pillars of modern physics, quantum mechanics and general relativity, in a way no one had previously imagined. If correct, it implies that the fabric of spacetime itself might be woven together by an unimaginably complex network of tiny quantum wormholes, with every entangled pair in the universe linked by its own invisible thread through the bulk of higher dimensions. This incredible convergence of ideas paints a picture where the largest conceivable structures in the cosmos and the smallest quantum phenomena might be two sides of the same coin. The dream of a traversable wormhole, a stargate allowing for near-instantaneous travel across the galaxy, remains firmly in the realm of speculation, a challenge that would require a mastery over physics and energy that borders on the godlike. Yet, the mere possibility that such structures could be consistent with the laws of physics and their deep theoretical connection to the quantum world forever changes our perspective on the universe. It suggests that the cosmos might be far more interconnected than it appears, with hidden tunnels woven into the very heart of reality, waiting to be understood. Yet, as we consider the grand cosmic structures and hidden dimensions that might define reality, we must also turn our attention to the very laws that govern the particles within it. The quest for a deeper, more unified understanding of physics has led to one of the most elegant and mathematically beautiful ideas in modern theoretical physics: supersymmetry. This is not just a minor tweak to our existing models, it is a profound extension of the fundamental principles of the universe, one that promises to solve some of the most stubborn puzzles in physics and could finally reveal the identity of dark matter. At its heart, supersymmetry, often nicknamed SUSY, proposes a stunning and deeply symmetric relationship between the two fundamental classes of particles that make up the universe, fermions and bosons. Fermions are the building blocks of matter, particles like electrons and quarks which come together to form atoms, molecules, and ultimately everything we can see and touch. Bosons, on the other hand, are the force carriers. They are the messengers that mediate the interactions between matter. The photon, for instance, is the boson that carries the electromagnetic force, while gluons carry the strong nuclear force that holds atomic nuclei together. What supersymmetry suggests is that this distinction is not absolute. It posits that for every known fermion, there must be a superpartner that is a boson, and for every known boson, a superpartner that is a fermion. This would create a perfect and elegant symmetry at the most fundamental level of nature. The electron, a fermion, would have a bosonic superpartner called the selectron. The photon, a boson, would have a fermionic superpartner called the photino. This doubling of the particle catalog isn't proposed arbitrarily. It emerges as a necessary and beautiful consequence of the mathematics when physicists attempt to combine gravity with the other fundamental forces. The implications of this symmetry are tremendous, chief among them a potential solution to the infamous hierarchy problem. This problem asks why the Higgs boson is so relatively light. The math of the Standard Model suggests that the Higgs should interact with other particles in such a way that its mass gets driven up to an enormous scale, near the Planck mass, which is a billion times heavier than the proton. This would make the formation of atoms, stars, and life impossible. Supersymmetry provides a graceful solution. For every particle that gives a large positive contribution to the Higgs mass, its superpartner gives an identical large negative contribution. These contributions cancel each other out with perfect precision, naturally protecting the Higgs mass and keeping it at the low value we observe. It's a mathematical balancing act of breathtaking beauty, where the universe's problems are solved not by adding complexity, but by introducing a deeper, more fundamental symmetry. Perhaps the most exciting implication for our cosmic mysteries is that supersymmetry provides a perfect candidate for dark matter. In most SUSY models, the lightest of all the proposed superpartners, often called the lightest supersymmetric particle or LSP, is stable. It would not decay into anything else because there is no lighter particle for it to decay into that also conserves something called R parity, a quantum number that distinguishes normal particles from their superpartners. This particle, frequently thought to be the neutralino, a mix of the superpartners of the photon, the Z boson, and the Higgs, would have been created in abundance in the heat of the Big Bang. It would be electrically neutral, interact only very weakly with normal matter, and have significant mass, ticking every box for a cold dark matter particle. For many physicists, this was too good to be a coincidence. It seemed like a clear signal that nature was guided by this sublime symmetry. This brings us to the great puzzle of modern particle physics. If supersymmetry is so elegant and solves so many problems, why haven't we found it? The Large Hadron Collider, the most powerful particle accelerator ever built, was designed in part to discover these superpartners. Physicists expected that at the tremendous energies the LHC could achieve, we would start to see these particles being created. The most straightforward and simplest versions of supersymmetry predicted that superpartners should appear at energy scales not too far above the Higgs mass. Yet, after years of collecting data from countless proton collisions, the detectors have found no definitive sign of selectrons, squarks, or neutralinos. The silence has been deafening, forcing a major re-evaluation within the field. This absence of evidence does not necessarily mean supersymmetry is wrong. It may mean that the symmetry is broken and the superpartners are much heavier than initially hoped. If the symmetry were perfect, superpartners would have the exact same mass as their Standard Model counterparts, and we would have detected them long ago. But in nature, symmetries can be broken. Think of a perfectly round pencil balanced on its point. The system has rotational symmetry, but that symmetry is broken the moment the pencil falls over to rest in one specific direction. In a similar way, supersymmetry might be a true symmetry of the laws of physics at the very highest energies, but it becomes broken at the lower energies of our everyday world. This breaking would give the superpartners their large masses, pushing them beyond the current reach of our colliders. The energy required to produce them might be just a little too high for the LHC, or perhaps far, far higher, awaiting a future, more powerful machine. The search is not over. It has simply shifted to hunting for indirect signs, subtle quantum effects that these heavy particles might impose on the particles we can see, or waiting for the next leap in our experimental capabilities to peer even deeper into the heart of energy and matter. The dream of supersymmetry, with its promise of a more complete and harmonious universe, remains one of the most compelling chapters in our ongoing quest to understand reality's hidden architecture. But if the search for supersymmetry pushes our particle colliders to their limits, our next theory takes us to the very edge of measurement itself, to a faint whisper of chaos that might be encoded in the fabric of spacetime. We are venturing into the realm of holographic noise, a fascinating prediction that our seemingly smooth and continuous reality is actually pixelated, buzzing with a fundamental quantum jitter. This idea flows directly from the holographic principle we explored earlier. If our three-dimensional universe is indeed a projection from a two-dimensional surface, then information about everything within that volume, every star, every person, every atom, must be encoded on the boundary. There's a fundamental limit to how much information can be stored in any given region of space, a limit defined by its surface area and not its volume. This creates a cosmic information bottleneck. It suggests that spacetime at the tiniest possible scale cannot be infinitely smooth. Just as a digital photograph appears smooth from a distance but reveals its pixelated grid when you zoom in too far, spacetime itself must have a granular structure. This granularity is not made of little cubes. It's a fundamental limit to the precision with which we can ever measure anything. This inherent fuzziness is what physicists call holographic noise. This noise is predicted to manifest at the Planck scale, an almost unimaginably small distance of about 10 to the power of -35 meters. At this scale, the very concepts of here and there break down. Space is not calm and still. It is a seething quantum foam, a chaotic frenzy where tiny virtual particles and wormholes blink in and out of existence. This isn't empty space, it's space at its most active and turbulent. According to the holographic principle, this isn't random chaos. It is the visual manifestation of the information being processed on the cosmic horizon, the projection flickering as the data is translated from 2 dimensions into 3. The jitter is the universe's resolution limit. The audacious question then becomes, if this noise is real, can we actually detect it? A team of physicists, including Craig Hogan of Fermilab, proposed a brilliant experiment to do just that using the most precise rulers ever built, gravitational wave interferometers. Instruments like LIGO and Virgo work by splitting a laser beam and sending the two halves down long, perpendicular arms several kilometers in length. The beams bounce off mirrors and are recombined. If a gravitational wave passes through, it will stretch one arm and squeeze the other by a minuscule amount, changing the distance each laser beam travels and creating an interference pattern in the recombined light. These detectors are so phenomenally sensitive they can measure changes in length thousands of times smaller than a proton. Hogan's insight was that holographic noise should also affect these measurements. The jitter at the Planck scale would mean the mirrors themselves are never perfectly still. Their precise location in space would be constantly, randomly fluctuating. If you could listen to the silence between gravitational wave events, you shouldn't hear perfect quiet. You should hear a faint, fundamental hiss, the sound of spacetime itself pixelating. This noise would have a specific signature, appearing equally in both arms of the interferometer regardless of their orientation, unlike a gravitational wave which has a specific polarization. The hunt for this signal is ongoing, pushing interferometer technology to its absolute breaking point. Initial analysis of data from the GEO 600 interferometer in Germany about a decade ago showed an unexplained, persistent noise that some, including Hogan, speculated could be this holographic jitter. While that specific signal was later largely ruled out, the quest continues. Newer, more stable tabletop interferometers are being designed specifically to listen for this universal background hum. Detecting it would be a paradigm-shifting moment in physics. It would be the first direct experimental evidence that the holographic principle is correct, providing tangible proof that our experienced reality is a projection. It would mean that the universe really is a kind of cosmic hologram, and that the true, fundamental description of nature is written on a distant, two-dimensional surface in a language of bits and pixels. We would have to radically rethink our place in the cosmos, not as beings living inside a container of space, but as patterns of information emerging from a vast cosmic screen. But if the seething quantum foam suggests a pixelated foundation for reality, our next theory tackles a question that has stumped physicists for a century. How does the blurry, probabilistic world of quantum possibilities transform into the single, solid reality we all experience? This is the notorious measurement problem, and one of the most compelling solutions is a theory known as quantum Darwinism. To grasp its elegance, we must return to that most baffling of quantum experiments, the double slit. When we're not looking, a single electron behaves like a wave, passing through both slits simultaneously and interfering with itself. But the moment we place a detector to see which slit it goes through, this wave-like behavior collapses. The electron is suddenly just a particle found at one slit or the other. The central question is, what exactly constitutes a measurement? What magical process forces the quantum potentiality to choose a single classical outcome? The traditional Copenhagen interpretation simply postulates that the act of observation by a conscious observer causes the collapse, but this raises more questions than it answers. Is a cat conscious? Is a bacterium? Where do we draw the line? Quantum Darwinism, developed by theorists like Wojciech, offers a far more robust and less mystical explanation. It argues that collapse isn't caused by consciousness, it's caused by the environment. In our daily lives, no quantum system is ever truly isolated. Every particle is constantly bombarded by photons of light, air molecules, and the faint whisper of background radiation. This constant interaction is the key. When a quantum system interacts with its environment, its fragile superposition, the state of being in multiple places or states at once, becomes entangled with countless particles in the surroundings. This process, called decoherence, Chinese letter, Chinese letter, Chinese letter, Chinese letter, Chinese letter, destroys the quantum coherence, effectively erasing the weird interference effects and making the system appear classical. But decoherence alone doesn't explain why we all seem to agree on what that single outcome is. This is where the Darwinism part of the theory comes in. Imagine a quantum system, say a particle that is in a superposition of spinning both clockwise and counterclockwise. When it interacts with a single photon from the environment, that photon becomes entangled with it, carrying away information about the spin. But one photon isn't enough to define reality. The revolutionary idea is that the environment isn't just a random disturbance, it acts as a replication machine for information. The particle doesn't just interact with one photon, it interacts with thousands, millions, billions of them. And crucially, only certain types of information about the quantum system are robust enough to be copied and recopied over and over into the environment without being scrambled. These special quantum states are called pointer states, and they are uniquely resistant to decoherence. They are the fittest states in a Darwinian sense. In our example, information about the particle having a definite spin, either clockwise or counterclockwise, is a robust pointer state. This information can be imprinted onto countless environmental photons. The information about it being in a fuzzy superposition, however, is fragile and gets destroyed immediately. As a result, the environment becomes filled with multiple, identical copies of the same classical information. You, as an observer, don't need to directly interact with the quantum particle itself to measure it. You simply need to intercept or sample just a few of the countless environmental photons that are all broadcasting the same message. This is why we all perceive the same objective reality. We are all independently sampling from the same vast reservoir of information that has been amplified and broadcast by the environment. The reason the moon is still there when nobody looks is because it is constantly interacting with sunlight, cosmic rays, and the solar wind, tirelessly advertising its position and state to the entire universe. This framework beautifully solves the measurement problem without invoking any special role for consciousness. The collapse is not a physical event but a transition in relationship. It's the point at which information about a specific outcome becomes so widely disseminated and redundantly encoded in the environment that it is effectively irreversible and available to any potential observer. Quantum Darwinism paints a picture of reality where objectivity emerges from the selective proliferation of information. The classical world we see is not the only possible outcome, but it is the one that was most fit to be copied. Our perception of a stable, single universe is a direct consequence of a natural selection process playing out at the quantum level, where only the fittest information survives to be observed. But if the holographic principle suggests that our three-dimensional reality is a projection from a two-dimensional surface, then the next theory asks an even more radical question. What if space-time itself, the very stage upon which the universe plays out, isn't fundamental at all? This is the startling proposition of emergent space-time, a concept that dismantles our most basic intuition about reality. We tend to think of space and time as the ultimate backdrop, the immutable container that existed before matter and energy and will persist after they are gone. But what if this container is an illusion? What if space and time are not the foundation of the universe, but rather a secondary phenomenon that emerges from something deeper, something more primitive and utterly non-spatial? This revolutionary idea finds its roots in the bizarre and counterintuitive world of quantum entanglement. Remember that spooky action at a distance that so troubled Einstein, where two particles can be instantaneously connected across vast cosmic distances. For decades, this was seen as a strange exception to the rule of locality, the principle that objects are only influenced by their immediate surroundings. But emergent spacetime theory flips this view entirely. It proposes that entanglement isn't a weird phenomenon that happens within space. Entanglement is what creates space. The geometric connection we perceive as empty space between 2 points might actually be built from an underlying web of quantum information links. The more entangled two systems are, the closer they are in this emergent geometric reality. It's as if the universe is a cosmic tapestry, and the threads weaving it together aren't made of fabric, but of quantum information and correlation. This perspective completely redefines our understanding of locality. In a universe with fundamental spacetime, two things are close because they occupy nearby coordinates. In a universe with emergent spacetime, two things are close because they are highly entangled. Distance becomes a measure of quantum connection, not a primary physical property. This explains the mystery of entanglement's instantaneity in a breathtakingly elegant way. If there is no fundamental space separating the particles, then there is no distance for information to travel across. The connectedness is primal, the illusion of separation is what comes later. This idea is powerfully captured by the ER equals EPR conjecture we touched on earlier, which suggests that every wormhole, a geometric bridge through space, is equivalent to a state of quantum entanglement. A tunnel through the cosmos and a spooky connection might be two different descriptions of the same underlying reality. So what could this deeper, non-spatial reality be like? If it's not space-time, what is it? Physicists working on this frontier, often using tools from quantum information theory, speculate that the fundamental level of reality might be a vast, chaotic network of interacting bits or qubits, a cosmic quantum computer. In this view, the universe at its core is not a place but a process. It is a seething, interconnected web of relationships where concepts like here and there have no meaning. The smooth, continuous spacetime we experience would then be a coarse-grained, approximate picture of this frenetic quantum activity, much like the smooth surface of a pond emerges from the chaotic motion of countless water molecules. Our perception of a calm, ordered universe is a useful illusion that emerges only when we look at the system from a distance, ignoring the microscopic details. The implications of this are nothing short of earth-shattering for our understanding of the Big Bang and the origin of the universe. If space-time is emergent, then the singularity at the beginning of time wasn't a point of infinite density in space. It was the moment when the quantum relationships beneath space-time first crystallized into the geometry we recognize. The Big Bang becomes less of a cosmic explosion and more of a cosmic phase transition, akin to water freezing into ice, where a formless quantum system suddenly organized itself into a universe with space and time. This provides a potential path to resolve the conflict between general relativity and quantum mechanics, not by forcing them together, but by showing that both are themselves emergent from a more fundamental theory where concepts like singularities simply don't exist. We are left with a humbling and magnificent vision. We do not live in a universe that is contained within space and time. We live within a universe that is itself an expression of something far more mysterious, a vast, interconnected quantum reality whose true nature we are only just beginning to glimpse. If the idea of our universe being born from a black hole seemed like a grand cosmic recycling program, then the next theory takes that concept and propels it into a breathtaking new dimension, proposing that the cosmos itself might be alive in a metaphorical sense, subject to the same evolutionary pressures that shape life on Earth. This is Lee Smollen's theory of cosmic natural selection, a profoundly provocative idea that suggests universes don't just exist, they evolve, compete, and reproduce, with black holes acting as the cosmic wombs for new generations. Smollen, a visionary theoretical physicist, asked a simple yet radical question: what if the fundamental constants of nature, the numbers that seem so perfectly fine-tuned for life, aren't fine-tuned at all? What if they are simply the result of a long and brutal process of cosmic evolution, where universes that are better at reproducing become more common? In this view, our universe isn't a one-off creation. It's the current product of an ancient lineage, one branch on a vast and growing tree of possible cosmos. The engine of this incredible process is the black hole. Smollen's theory hinges on a fascinating and elegant mechanism. When a massive star collapses into a black hole, the extreme conditions at the singularity, a point of infinite density where the known laws of physics break down, might provide the perfect environment for a new universe to be born, budding off from our own with its own slightly modified set of physical laws and constants. This isn't a process we could ever observe from within our universe. The new cosmos would be entirely separate, expanding into its own dimensions, hidden forever behind the event horizon of the parent black hole. But in that moment of creation, a tiny, random mutation could occur in the fundamental parameters. Perhaps in this new universe, the strength of the strong nuclear force is a fraction of a percent weaker. In another, the mass of the electron is minutely different. Each black hole collapse becomes a roll of the cosmic dice, producing not an identical offspring, but a universe with subtle variations, a child with its own unique physical identity. This is where the concept of natural selection enters the picture. For evolution to work, there must be variation, heredity, and a selection pressure. The variation comes from the random mutations at the singularity. Heredity comes from the fact that the offspring universe would likely inherit most of its parameters from its parent, just as a child inherits most genes from its parents. The selection pressure is where it gets truly fascinating. What trait would be most favored by cosmic evolution? According to Smollen, it is fecundity, the ability to produce as many offspring as possible. And what is the primary mechanism for producing offspring in this model? Black holes. Therefore, universes that have physical constants which are optimal for producing the maximum number of black holes would be the most reproductively successful. They would leave behind more progeny, and over countless generations, the population of universes would become dominated by those with black hole-friendly parameters. This provides a stunning and elegant explanation for the mystery of fine-tuning without needing to invoke a designer or an infinity of parallel worlds. Why is our universe so good at making black holes? Because we are the descendants of a long line of universes that were excellent at it. And here's the truly beautiful part. The conditions that make a universe prolific at producing black holes are strikingly similar to the conditions that allow for the existence of life. To form a black hole, you first need stars. Stars form from the gravitational collapse of clouds of hydrogen and helium. They burn for billions of years through nuclear fusion, creating heavier elements like carbon and oxygen in their cores, which are then scattered across the galaxy when the stars die. Some of these dead stars then collapse into black holes. The very same processes the formation of long-lived stars, and the nuclear fusion that forges the elements of life are prerequisites for both black hole production and for us. So, we don't live in a universe that was designed for life. We live in a universe that was selected for its ability to make black holes, and we are a fortunate byproduct, a kind of cosmic spillover that emerges from these fertile conditions. This vision of a cosmos evolving over deep time is both humbling and magnificent. It suggests a vast, branching tree of universes, a true cosmic phylogeny. Our universe is not alone. It has parents, siblings, and cousins, each with their own unique physical laws. Some branches might be barren, with constants that prevent star formation entirely, ending that particular lineage. Other branches might be wildly successful, filled with galaxies that produce black holes at an astonishing rate. We find ourselves on a fruitful branch, one where the constants allow for both the creation of cosmic engines of reproduction and the delicate chemistry of life. Lee Smollen's theory transforms the cosmos from a static, lifeless arena into a dynamic, ever-changing ecosystem, where the laws of physics themselves are not eternal decrees but temporary adaptations, honed over eons of trial and error in the greatest evolutionary story ever told. Yet even the silent, cold demise of heat death might be a preferable fate to the cataclysm waiting in one of the darkest corners of cosmological theory, a scenario so violent it would dismantle the universe from the largest galaxies down to the very atoms in your body. This is the phantom energy scenario, an extreme and terrifying variant of dark energy that could lead to the absolute annihilation of everything in a final event known as the Big Rip. To understand how this could happen, we need to look at the key parameter cosmologists use to classify dark energy, the equation of state, represented by the letter W. This is essentially a number that describes the relationship between the pressure and density of dark energy. For the standard cosmological constant that Einstein proposed, this value is exactly -1. This produces a constant, gentle acceleration that eventually leads to the quiet isolation of heat death. But what if W is not exactly -1? What if it is something even more negative, something less than -1? This is the realm of phantom energy, a substance with such powerfully negative pressure that its repulsive gravitational force doesn't just remain constant, it actually grows stronger over time as the universe expands. The implications of this are as profound as they are horrifying. In our current universe, despite the accelerating expansion, various forces are still able to hold structures together. Gravity binds galaxies and galaxy clusters. The electromagnetic force holds stars, planets, and you yourself intact. But if dark energy is phantom energy, this delicate balance is doomed. As the universe expands, the density of phantom energy doesn't decrease like normal matter or radiation. It increases. More space creates more phantom energy, which creates even stronger repulsive gravity, which pushes space to expand even faster in a terrifying feedback loop of accelerating acceleration. For billions of years, this might not be noticeable. The expansion would gradually accelerate, but the cosmic structures would hold. Galaxy clusters would be the first to go. Their mutual gravitational pull, which has held them together for eons, would eventually be overcome by the escalating repulsive force of phantom energy. They would be ripped apart, their constituent galaxies flung away from each other into the ever-darkening void. Next would come the galaxies themselves. The gravitational glue holding stars together around a central black hole would be no match for the phantom force. Each star would be torn from its galactic family and sent flying off on its own. Then the end would come for individual solar systems. The Sun's gravitational hold on Earth and the other planets would be severed, but the true horror would come in the final moments. As the phantom energy density grows infinite in the last frantic minutes before the big rip, its repulsive force would surpass not just gravity, but every fundamental force in nature. It would overcome the electromagnetic force that binds atoms together. Every molecule, every atom would be torn apart. Protons and electrons would be ripped from each other. In the last fraction of a second, the very fabric of space-time itself would be shredded. The bonds holding atomic nuclei together, the strong nuclear force, the most powerful force we know, would be vanquished. Quarks would be separated from each other. According to some calculations, in the final instant, the universe would reach a state of infinite expansion and infinite energy density, a singularity of tearing rather than crushing, where the concept of physics itself ceases to have any meaning. Is this our actual fate? Current observational evidence offers a sliver of hope. Astronomers use a variety of tools: distant supernova, the cosmic microwave background, the large-scale structure of galaxies, to measure the equation of state parameter W with ever-increasing precision. The best data we have from missions like Planck strongly suggests that W is very, very close to -1, consistent with a simple cosmological constant. The constraints are tight. It appears there is no room for W to be significantly less than -1. For now, the phantom energy scenario remains a theoretical specter, a haunting possibility that the laws of physics allow, but that our universe seems to have mercifully avoided. It stands as the most ultimate and absolute cosmic doom imaginable, a reminder of the incredible precarity of our existence and the profound power of the dark forces that shape our universe's destiny. But if the vast majority of quantum interpretations treat the wave function as a real, physical thing, our next theory proposes a dramatic shift in perspective, suggesting that the heart of quantum mechanics isn't about reality at all, but about our own personal beliefs. This is quantum Bayesianism, or cubism for short, an interpretation that boldly declares that the probabilities at the core of quantum theory do not describe an objective world, but instead represent an individual agent's subjective degrees of belief. In this view, quantum mechanics is not a direct picture of the universe's inner workings. It is a tool, a meticulously crafted guidebook that tells a user, any user, how to navigate the world and update their personal expectations based on their interactions with it. To grasp this, think about a simple, everyday forecast. When a meteorologist says there's a 70% chance of rain, they aren't describing an objective state of the atmosphere that is 70% rainy. They are quantifying their own confidence, their personal belief, based on the data from their models. The rain itself will either happen or it won't. The probability is a measure of the forecaster's uncertainty, not a property of the weather. Cubism applies this exact same Bayesian, subjective logic to the quantum realm. When a quantum mechanic says an electron has a 50% chance of having spin up, they are not describing an electron that is objectively in a fuzzy mixture of states. They are simply stating their own personal, subjective expectation for what will happen when they eventually measure it. The wave function is not a physical field. It is a mathematical representation of an agent's state of knowledge, a catalogue of their best, most informed bets about future experiences. This radically subjective starting point provides an incredibly elegant and personal resolution to some of quantum mechanics' most infamous paradoxes. Take Schrödinger's cat. The standard interpretation presents us with the deeply unsettling image of a cat that is simultaneously alive and dead until someone opens the box. From a cubist perspective, this is a confusion of categories. The wave function describing the superposed cat does not represent the cat's objective condition. It represents the user's state of uncertainty about what they will find upon opening the box. The cat itself is either definitively alive or definitively dead the entire time. The quantum weirdness isn't in the system, it's in the head of the observer who lacks the information. The act of opening the box isn't a physical collapse of a wave. It is a moment of personal discovery where the agent simply updates their beliefs to match the new, definite reality they have encountered. This framework extends beautifully to the measurement problem. In cubism, there is no mysterious, undefined moment of collapse where a quantum system suddenly chooses a state. Instead, a measurement is simply the moment an agent interacts with the world and gains a new experience. This experience is personal and unique to that agent. It forces them to dramatically revise their wave function, their internal catalogue of expectations, to incorporate this new piece of information. The update is sudden and drastic because the experience itself is definitive. You either see a live cat or a dead one. There is no longer a paradox about what causes the collapse because the wave function was never a real thing out in the world to begin with. It was always just a tool inside the agent's mind, and it gets updated the same way any belief does when confronted with new evidence. This makes every measurement an intimate event, a moment of learning that is specific to the person doing the measuring. For this reason, cubism is often described as a psychological or even a personally solipsistic approach to quantum foundations. It places the focus squarely on the experience of the individual user of quantum theory. However, its proponents are quick to counter that this does not lead to a chaotic world where everyone creates their own reality. While the probabilities are subjective, the experiences that force us to update them are not. Reality kicks back, and it kicks back with consistency. If I measure an electron spin, I might have assigned a 50% probability to the outcome, but the actual result I get is a brute fact, an undeniable experience that happens to me. Furthermore, if I then tell you the result, that communication becomes a new, undeniable experience for you, forcing you to update your own personal wave function. The world may not be made of waves and particles in the classical sense, but it is made of stable, shared experiences that allow us to communicate, build instruments, and develop a common, objective-seeming science. The objectivity we see emerges from a shared subjectivity, from a consensus built upon countless individual experiences and communications. This perspective also demystifies the spookiness of quantum entanglement. In the cubist view, when two particles are entangled, it simply means that the beliefs of an agent about the outcomes of measurements on the two particles are correlated. If I know nothing about two electrons except that they are entangled, my probability assignments for their spins are linked. Learning the result of a measurement on one electron immediately tells me what result I should expect for the other. This doesn't require any mysterious, instantaneous influence traveling between them. It only requires that my beliefs be internally consistent. The update is instantaneous in my mind, not in the world. The particles themselves may have had definite properties all along. I just didn't know them. Cubism severs the uncomfortable connection between measurement and action at a distance, relocating the puzzle from the fabric of spacetime to the logic of personal expectation. By reframing quantum mechanics as a theory of subjective probability, cubism offers a profoundly human-centric vision of science. It suggests that quantum mechanics is not a description of a bizarre external reality, but a formalization of the process of learning and making decisions in a world that is inherently unpredictable at its core. It tells us that the fundamental uncertainty of the quantum world is not a flaw in our knowledge, but a permanent feature of our relationship with the universe. We are not passive observers of a predetermined clockwork mechanism, but active participants constantly engaging with reality, gathering experiences, and refining our own personal guidebooks for what might happen next. In the cubist universe, science becomes a conversation between the agent and the world, a dynamic and personal journey of discovery where the probabilities are not in the atoms, but in us. But if emergent spacetime suggests the universe is fundamentally built from a web of quantum information, then the next theory takes a starkly different path, proposing that the deepest level of reality is not smooth, not continuous, but granular, a universe built from discrete, indivisible atoms of spacetime itself. This is causal set theory, an approach to quantum gravity that is as philosophically minimalist as it is mathematically audacious. Its core premise is breathtakingly simple. The fundamental structure of the universe is not a smooth, four-dimensional continuum, as Einstein described, but a vast collection of discrete, point-like events. Think of these events as the most basic moments of happening, the universe's irreducible atoms of occurrence, but a random pile of sand is not a sculpture. What gives this collection its structure, what turns it from a heap into a universe, is not their position in space or time, but the causal relationships between them. The entire theory is built on two foundational principles. First, spacetime is discrete. There is a smallest possible unit of volume and time, preventing the infinities that plague other theories. Second, all that matters physically are these causal relations. If one event can influence another, they are linked. This network of cause and effect is the sole source of the universe's geometry. Everything else, the distance between events, the flow of time, is a secondary, emergent property. This approach provides a stunningly elegant solution to one of the most vexing problems in physics: the singularity at the heart of a black hole and at the beginning of the Big Bang. In general relativity, these are points of infinite density where the equations break down and predictability is lost. But in a causal set, there are no infinities because the set is discrete. There is only a finite number of elements preceding any given event. The Big Bang is no longer a singularity. It is simply the very first event, the foundational element from which all other events descend. It has no predecessor, which is why we can't ask what came before, but it is not a point of infinite anything. It is just the start of the chain. Similarly, a black hole singularity is smoothed out into a final, dense cluster of events from which no further influence can emerge. By building the universe from discrete blocks, causal set theory naturally avoids the mathematical pathologies that have haunted physics for a century. The true magic of the theory, however, lies in how this sparse, abstract structure, just a set of points with a partial ordering, manages to conjure forth the rich, continuous spacetime we all experience. The key is a beautiful phenomenon known as spacetime from causality. Imagine a vast, chaotic crowd of people. Now, imagine you only know one thing about them: who is whose ancestor. You don't know how far apart they live, you don't know their ages, just the family tree of who came before whom. From that web of relationships alone, you could start to make surprisingly accurate guesses about their relative ages and a rough sense of generational distance. Causal set theory proposes that the universe works in a similar way. The continuous dimensions of space and time, and even the Lorentz invariance that is the cornerstone of Einstein's relativity. The fact that the laws of physics are the same for all observers moving at constant velocity are all approximate, large-scale illusions that emerge from the underlying causal network. This is a profound and radical form of background independence. The theory doesn't assume a pre-existing stage of spacetime for its elements to live on. The stage itself is built by the relationships between the elements. The universe isn't in space and time, it is the causal set, and space and time are its shadows. For this to work, the emerging reality must respect the symmetries of special relativity, and here causal set theory faces its greatest challenge and its most brilliant triumph. The theory must show how an approximately smooth, four-dimensional Lorentzian manifold can condense out of a discrete graph-like structure. The astonishing answer lies in a concept called sprinkling. How do you get from a discrete set to a continuous-looking reality? You take the set of causal elements and you sprinkle them into a region at random, with a density that corresponds to one element per unit volume of the Planck scale. This random sprinkling is crucial because it generates a structure that, on large scales, is fundamentally Lorentz invariant. A Lorentz transformation, like changing your state of motion, will jumble up your perception of space and time, but it preserves causal relationships. If event A can influence event B in one frame, it can in all frames. Since the causal set is defined only by these relationships, its fundamental structure looks the same to all observers regardless of their motion. The smooth geometry and the symmetry of relativity aren't put in by hand. They emerge naturally from the randomness of the sprinkling and the invariance of the causal order. It's a breathtakingly simple and powerful mechanism. The universe's commitment to causality alone guarantees that the spacetime which emerges will respect Einstein's principles. Despite its compelling elegance, causal set theory, like all approaches to quantum gravity, is a work in profound progress. The central challenge is one of dynamics. How does this cosmic network of events actually evolve? What is the law of motion for the causal set? Theorists are exploring ideas inspired by quantum mechanics, where the history of the universe is not a single, fixed causal set, but a quantum superposition of all possible causal sets. The amplitude for any particular history to be real would be determined by a sum over all possible paths it could take, a vast cosmological analog of the quantum paths of a particle. The ultimate goal is to derive from these first principles the equations of general relativity, not as fundamental laws, but as an effective, large-scale approximation. Much like the law of pressure emerges from the chaotic motion of molecules, even though no single molecule has pressure. The journey of causal set theory is a journey to see the universe not as a continuous flowing river, but as a cascade of individual droplets whose collective rhythm creates the irresistible and beautiful illusion of a stream. Yet even the most cataclysmic cosmic destruction pales before a paradox that strikes at the very heart of physics itself, a puzzle so profound it threatens to unravel our understanding of reality from the inside out. We now arrive at the infamous black hole information paradox, a problem that has pitted the two great pillars of modern science, quantum mechanics and general relativity, against each other in a conflict with seemingly no resolution. The story begins with a foundational principle of quantum mechanics, unitarity. This is the idea that information, the distinct identity of every particle and its state, can never be truly lost. It can be scrambled, spread out, and become incredibly difficult to read, like a book thrown into a fire whose ashes are scattered to the wind. But in principle, a being with infinite knowledge and power could always reverse the process and reconstruct the book. Every interaction is reversible, information is forever. For decades, it seemed general relativity offered a glaring exception to this sacred rule in the form of a black hole. Imagine a daring astronaut, let's call her Alice, who takes a plunge into a stellar mass black hole, carrying with her a book containing a vast amount of information, perhaps the complete digital code of every video on this channel. From the perspective of an outside observer, Bob, watching from a safe distance, something bizarre happens due to the extreme gravitational time dilation at the event horizon. He sees Alice's image slow down, redden, and eventually fade away, seemingly frozen just outside the point of no return. It appears to Bob that all the information about Alice and her book is smeared across the surface of the black hole, preserved there forever. But from Alice's perspective, she crosses the event horizon uneventfully. her and her book's information continuing intact into the black hole's interior. So far, so good. The information exists in two places, on the horizon for Bob and inside for Alice. No law of physics is broken yet. The paradox was born from Stephen Hawking's stunning realization in 1974 that black holes are not actually black. Applying quantum theory to the curved spacetime around an event horizon, he showed that pairs of virtual particles, one with positive energy, one with negative energy, constantly flicker into existence and normally annihilate each other. But at the very edge of a black hole, this delicate dance can be disrupted. The negative energy particle can fall into the black hole, while its positive energy partner escapes into space. To an outside observer like Bob, this stream of escaping positive energy particles looks like a faint thermal glow, now known as Hawking radiation. The negative energy particle that fell in reduces the black hole's mass by a tiny amount. Over eons, this process causes the black hole to slowly evaporate, eventually vanishing completely. And here lies the catastrophic problem. Hawking radiation is purely thermal. Its properties depend only on the black hole's mass, charge, and spin. It contains no information whatsoever about what fell into the black hole. It doesn't matter if the black hole was formed from a collapsed star, a cloud of gas, or a library of books. The Hawking radiation it emits is identical. When the black hole finally evaporates, all that remains is this random thermal radiation. The specific, unique information about Alice and her book has been irretrievably lost. The universe has taken a complex, low-entropy state, the detailed arrangement of particles that was Alice, and transformed it into a random, high-entropy state, the featureless Hawking radiation. This violates quantum unitarity, the non-negotiable rule that information must be preserved. Hawking himself declared that this meant even quantum mechanics had to be revised, a conclusion that horrified many physicists who saw it as an unacceptable sacrifice. This set the stage for the Black Hole War, a decades-long intellectual battle between Hawking on one side and physicists like Leonard Susskind and Gerard T. Hooft on the other, who were determined to find a way to save the information. The war seemed to escalate with the proposal of an even more violent paradox, the firewall. If information is to be saved, it must somehow be encoded in the Hawking radiation. This means the particles escaping late in the black hole's life must be subtly entangled with the particles that escaped early on, preserving the overall information. But for this to work, the late-emitted radiation must also be entangled with its partner particle that fell into the black hole long ago. This creates an impossible situation. A fundamental rule of quantum mechanics, the monogamy of entanglement, states that a particle cannot be fully entangled with two different systems at the same time. The outgoing Hawking radiation cannot be simultaneously entangled with its infalling partner and with the earlier radiation. To resolve this, physicists Ahmed Olmary, Donald Marolf, Joe Polchinski, and James Sully proposed a horrifying solution. The entanglement must be violently broken at the horizon. This rupture would release an enormous amount of energy, transforming the peaceful event horizon into a blazing wall of fire, a firewall, that would instantly incinerate any astronaut like Alice the moment she tried to cross. This solution saves information but blatantly violates Einstein's principle of equivalence, which states that falling through an event horizon of a large black hole should be a smooth and uneventful experience. You can't have both. The most promising escape from this impossible choice and the current leading resolution to the paradox brings us back to the holographic principle. The idea is that the information never actually makes it into the black hole's interior in the first place. Just as Bob observed from the outside, all the information contained in anything that falls in is rapidly scrambled and encoded onto the two-dimensional surface of the event horizon. The three-dimensional interior we imagine is a projection, a hologram generated from this data on the surface. When Hawking radiation is emitted, it is not random. It carries away that very information, slowly and carefully decoding the holographic plate. The information was never lost. It was just translated into an incredibly complex and scrambled form, much like the information on a DVD is encoded in a pattern of pits on a disk. To an outside observer, the black hole is a quantum information processor, not a cosmic shredder. This preserves unitarity without requiring a firewall, because from the outside perspective, there is no interior to fall into. Alice's information is on the surface, and her journey inward is part of the holographic illusion. Recent developments, particularly in the study of wormholes within the framework of quantum gravity, have provided a stunning geometric picture for how this information escape might work. The ER=EPR conjecture suggests that the entangled particles of Hawking radiation might be connected by microscopic wormholes, Einstein-Rosen bridges, through a higher dimensional space. These wormholes provide a hidden pathway for information to be transferred between the radiation particles, allowing them to become correlated without violating any quantum rules. The interior of the black hole might not be a separate place, but simply the geometric manifestation of the entanglement between all the Hawking radiation particles. This breathtaking vision unites the black hole, its radiation, and the fabric of spacetime into a single, deeply interconnected quantum system, finally offering a path to reconcile the war between gravity and quantum mechanics and preserve the integrity of information in our universe. Yet, even as cubism offers a radically subjective solution to the measurement problem, another interpretation makes an even more astonishing claim, placing human consciousness itself at the very center of the quantum drama. This is the von Neumann-Wigner interpretation, the provocative idea that it is not any physical interaction, but the act of conscious awareness that finally forces the quantum world to choose a definite state. The mathematical foundation for this audacious proposition was laid by the brilliant Hungarian-American physicist and polymath John von Neumann. In his groundbreaking 1932 book, The Mathematical Foundations of Quantum Mechanics, he presented a meticulous and comprehensive formulation of the entire theory. A key part of this work involved analyzing the process of measurement, breaking it down into a chain of interactions. Imagine a quantum system like an electron with an uncertain spin. To measure it, it must interact with a measuring device, perhaps a Geiger counter. That device then interacts with a recorder that prints a result, which is then observed by a human eye, and the signal is finally processed by a human brain. Von Neumann argued that this chain could, in principle, be described as one long, continuous quantum mechanical process. The entire system, electron, device, recorder, eye, and brain, could be treated as a single, gigantic wave function evolving in a superposition. The mathematics allowed for this chain to be cut at any point. You could say the collapse happens when the electron hits the device or when the device activates the recorder. But von Neumann pointed out that there was no clean mathematical reason within the theory itself to choose where to make that cut. The equations were consistent all the way up the chain. This led to a startling possibility. If the chain isn't broken by any physical interaction, the only place left to break it is at the point where it finally enters the subjective experience of a conscious observer. The collapse, he suggested, must happen in the mind. This abstract idea was later popularized and championed by von Neumann's friend and fellow Nobel laureate, Eugene Wigner, who crafted a deeply unsettling thought experiment to illustrate its implications. It's a variation on the classic Schrödinger's cat scenario, but with an even more personal twist. Imagine Wigner has a friend in an isolated laboratory. The friend is about to perform the double-slit experiment on a single particle. From Wigner's perspective, outside the lab, the entire system, the particle, the laboratory equipment, and even his friend is described by a single wave function. Until he opens the door to ask what happened, that entire lab exists in a superposition. For Wigner, his friend is in a state of being both someone who has seen the particle go through the left slit and someone who has seen it go through the right slit. But now, step inside the lab. From the friend's own perspective, the moment she made the measurement, the particle's wave function collapsed. She obtained a definite result. She has a single, clear memory of the outcome. So, who is right, Wigner outside, who describes his friend as being in a blurry superposition, or the friend inside, who is certain of her own experience? If the von Neumann-Wigner interpretation is correct, then both descriptions are valid until Wigner consciously interacts with his friend. The moment Wigner opens the door and asks for the result, his own conscious observation collapses the immense wave function encompassing the entire laboratory, forcing the entire reality, including his friend's memories, to snap into a single, consistent state. Until that moment, there is no objective fact of the matter about what the friend observed. Her conscious experience is not privileged. It too is suspended in quantum limbo until observed by someone else. The implications of this are nothing short of metaphysical. It suggests that consciousness is not a passive byproduct of physical processes in the brain, but an active participant in shaping reality. The universe would then be divided into two realms: the quantum domain, which is a realm of fuzzy potentialities, and the classical world, which is brought into concrete existence by the act of conscious observation. In this view, reality remains in a state of suspended animation, a world of maybes, until a mind looks at it and makes it so. This would resolve the paradox of Wigner's friend by declaring that the friend's own consciousness is what collapsed the wave function for her, but from Wigner's external perspective, that collapse is not complete until his consciousness confirms it. It introduces a strange kind of relativity of reality itself, dependent on the perspective of the conscious observer. Despite its philosophical allure, the von Neumann-Wigner interpretation is overwhelmingly rejected by the vast majority of physicists today. The objections are both practical and philosophical. First, it creates an arbitrary and problematic division between what is conscious and what is not. Does a cat have enough consciousness to cause collapse? What about a dog, a mouse, a bacterium, a sophisticated AI? This leads to a slippery slope with no clear demarcation line, an unscientific vagueness that physics strives to avoid. Second, it seems to make the entire enterprise of science solipsistic. If reality requires a conscious observer to become definite, what was the state of the universe before the first conscious beings evolved? Was the entire cosmos just a hazy superposition for billions of years, waiting for life to emerge to look at it and crystallize it into existence? This is a deeply unsatisfying proposition for a field that seeks objective, observer-independent truths about nature. Finally, and most decisively, modern experiments have provided powerful evidence for observer-independent collapse through the process of decoherence. As we explored with quantum Darwinism, the interaction with a surrounding environment, a single photon or a stray air molecule, is sufficient to destroy quantum coherence and make a system behave classically, long before any conscious being gets involved. The environment acts as a continuous and ubiquitous observer, constantly measuring the world and creating objective facts without any need for a mind. This renders the special role for consciousness unnecessary. We are not the creators of reality through our observation. We are simply latecomers who learn about a reality that has already been made definite by its own constant interactions. The von Neumann-Wigner interpretation remains a fascinating historical footnote, a bold and imaginative attempt to solve the measurement problem that ultimately failed to convince the scientific mainstream, not because it was illogical, but because a simpler, more elegant, and less anthropocentric explanation was found in the natural processes of the world itself. But if the idea of a universe built from discrete causal events feels abstract, prepare for a theory that makes this granularity its central mathematical mission. A framework that doesn't just suggest spacetime is pixelated, but actually calculates the precise size of those pixels. This is loop quantum gravity, or LQG, a bold and ambitious competitor to string theory in the quest to unify general relativity and quantum mechanics. While string theory proposes that the fundamental objects are tiny vibrating strings existing within spacetime, LQG takes a radically different path. It asks, what if spacetime itself is not the stage but one of the actors? What if it is not smooth and continuous but woven together from individual, discrete threads? The core innovation of LQG is its focus on the geometry of gravity itself. In Einstein's general relativity, gravity is not a force in the traditional sense. It is the curvature of spacetime, a bending of the stage upon which physics plays out. Loop quantum gravity takes this idea and makes it quantum. It seeks to quantize this geometry to find the smallest possible atoms of space and time. The theory gets its name from its fundamental building blocks, tiny, one-dimensional loops of gravitational field. Imagine the fabric of reality not as a smooth sheet, but as an incredibly fine mesh, a network of these woven loops. These loops aren't embedded in space, they are space. Where they intersect and link together, they create a structure known as a spin network, a mathematical graph that defines the quantum state of geometry itself. Each node in this network represents a tiny, discrete volume of space, and the links between them represent the quantized area that separates them. In this breathtaking vision, the universe is fundamentally a vast, evolving web of relationships, a cosmic network where concepts like here and there are defined by how the nodes are connected, not by any pre-existing coordinate system. This discrete foundation provides an elegant and powerful solution to one of the most intractable problems in all of physics, the singularity. In both the center of a black hole and at the beginning of the Big Bang, the equations of general relativity predict a point of infinite density and curvature, a place where the laws of physics simply give up. Infinities in physics are almost always a sign that a theory is incomplete, that we are missing a crucial piece of the puzzle. LQG naturally banishes these infinities because its building blocks are discrete. There is a smallest possible volume and a smallest possible area defined by the Planck scale. You cannot compress space into an infinitely small point because you eventually run into the smallest quantum of volume, much like you cannot divide a screen beyond its individual pixels. This means that as matter is crushed under its own gravity, the repulsive force arising from the quantum nature of geometry itself becomes overwhelming, preventing a true singularity from ever forming. This leads to one of the most profound and beautiful predictions of the theory, the Big Bounce. Instead of a universe born from a singular, infinitely dense point in a one-time creation event, LQG suggests a cyclical cosmos. In this model, our universe could be the latest in an endless series. Picture a previous universe, perhaps similar to our own, undergoing a phase of gravitational collapse. As it contracts, densities and temperatures soar to incredible levels. But just as it seems destined to crush itself into a singularity, the quantum gravitational repulsion kicks in. The collapse is halted, reversed, and the universe rebounds in a tremendous, explosive event, a Big Bang that is also a big bounce, giving birth to a new expanding universe from the ashes of the old one. This elegant idea replaces the terrifying, unknowable singularity with a cosmic transition, a turning point governed by physical law. It offers a potential answer to the ancient question of what came before the Big Bang, another universe on the other side of the bounce. The theory also makes a concrete, testable prediction that area and volume are quantized. Just as light comes in discrete packets called photons, the very geometry of space comes in discrete, indivisible units. The smallest possible unit of area, a Planck area, is about 10 to the power of -70 square meters. The smallest unit of volume is a Planck volume, even smaller. This means that if you could somehow measure the surface area of an object with unimaginable precision, you wouldn't find a smooth curve, you would find that the area is always a multiple of this fundamental unit. It would be like looking at a digital image. From a distance it looks smooth, but zoom in far enough and you see the individual pixels. While directly probing the Planck scale is far beyond our current technology, some physicists are looking for indirect signatures of this spacetime granularity, perhaps in the way ultra-high-energy cosmic rays interact with the fabric of reality, or in subtle imprints on the cosmic microwave background radiation. Finding evidence for this quantum foam would be a monumental validation of this profound and geometric vision of reality. But if we're reimagining the very fabric of spacetime as a dynamic quantum structure, then our next theory proposes one of the most exotic and bizarre possibilities of all, that the vacuum of space itself could be a supersolid. This isn't just empty nothingness, it's a state of matter that combines two seemingly contradictory properties. Imagine a material that has the rigid, crystalline structure of a solid diamond, yet can also flow forever without any friction or viscosity, like a perfect superfluid. This is the paradoxical nature of a supersolid, a state that has been created in laboratory experiments with ultra-cold atoms. Now take that concept and apply it to the very foundation of reality. Supersolid vacuum theory suggests that spacetime is not an inert stage, but is itself a cosmic-scale supersolid, a medium with a fixed, lattice-like structure that simultaneously allows for the effortless, frictionless flow of energy and matter. This radical idea provides a stunningly elegant potential explanation for the greatest mystery in modern cosmology, dark matter. If the vacuum has a crystalline structure, then it can't be perfect. Just like any crystal, it will have defects, tiny imperfections in its orderly grid. These could be point-like defects or dislocations in the fabric of spacetime itself. According to this theory, these vacuum defects would have mass. They would warp the geometry of space around them, creating a gravitational pull, but they would not interact with light or any other electromagnetic force because they are flaws in the stage, not actors upon it. This means they would be completely invisible, detectable only through their gravity. Sound familiar? These defects would behave exactly like the mysterious dark matter that holds galaxies together. In this view, dark matter isn't a cloud of exotic particles we haven't found. It's the ghostly gravitational imprint of the cracks and imperfections in the crystalline structure of spacetime. We are not searching for a particle, but for the grain of the universe's architecture. This framework also offers a compelling new perspective on gravity itself. Einstein's general relativity is incredibly successful, but it describes gravity as a smooth, continuous curvature of a featureless spacetime. If spacetime is actually a supersolid with a discrete structure, then our equations for gravity might need to be modified, especially at the very largest cosmic scales. The presence of these vacuum defects could subtly alter how gravity behaves over immense distances, potentially explaining why galaxies rotate too fast without needing to invoke vast halos of invisible matter. The modified behavior wouldn't be due to new particles, but to the underlying graininess of reality asserting itself. It's a profound shift. Instead of gravity being a force mediated by particles within space, it becomes an emergent property of the spacetime medium's own structure and its defects. The beauty of this theory lies in its connection to well-understood physics here on Earth. Condensed matter physicists study how phenomena like sound waves and heat conduction work in regular crystals and superfluids. Supersolid vacuum theory uses these solid ground experiments as a powerful analogy for the cosmos. Ripples in the rigid structure of this spacetime supersolid could manifest as gravitational waves. The frictionless flow of the superfluid component could explain the effortless motion of galaxies through the void. We can use our knowledge of how defects form in supercooled helium to make predictions about how dark matter should be distributed throughout the universe. This approach doesn't require inventing entirely new physics from whole cloth. It suggests that the laws governing the universe's largest scales might be a grand cosmic echo of the laws we discover in our most delicate laboratory experiments. It proposes that the vacuum of space is the most interesting and complex thing in the universe, not simply the empty stage upon which the drama of matter plays out. But if the universe possesses a fundamental structure that prevents paradoxical scenarios, then our next investigation takes us to the very edge of causality itself, to the notorious puzzles that have fueled science fiction for decades. We are now exploring the fascinating physics of temporal paradoxes and the elegant principles that might resolve them, ensuring the universe remains a logically consistent place even in the face of time travel. The most famous of these is the grandfather paradox. Imagine you build a time machine, travel back to the past, and prevent your own grandfather from meeting your grandmother. This would seemingly erase your own existence, which then begs the question, if you were never born, how could you have traveled back in time to stop the event in the first place? It is a closed loop of cause and effect that appears to tear logic apart at the seams. One compelling resolution comes from Russian physicist Igor Novikov, who proposed the self-consistency conjecture. Novikov's principles state that the laws of physics simply will not allow paradoxes to occur. If time travel to the past is possible, then any actions taken by the time traveler must have already been a part of history. Your journey to the past is not a new event that changes the timeline. It is an event that always happened. In this view, the universe is a single, self-consistent, and immutable block. You might travel back with the intention of stopping your grandfather's meeting, but something will always prevent you from succeeding. Your gun might jam, you might trip at the crucial moment, or you might simply change your mind upon seeing him. Your actions in the past can only ever be those that lead to the future from which you came. The timeline is fixed, and free will for the time traveler is an illusion. They can only ever do what they already did. This transforms the grandfather paradox from a logical impossibility into a predestination puzzle, where the time traveler becomes an unwitting agent in ensuring their own history unfolds exactly as it always has. Quantum mechanics offers another, even more mind-bending way out through the many worlds interpretation. In this framework, every quantum decision spawns a new parallel universe. Apply this to time travel and the paradox evaporates. When you step into your time machine and journey to the past, you are not traveling into your own history. You are crossing into the past of a parallel, branching universe that is nearly identical to your own up to the moment you arrived. In this new branch, you are free to do anything you want, including preventing that universe's version of your grandfather from meeting your grandmother. This action does not erase you from existence. It simply creates a new timeline where you were never born, while your original timeline and your original self remain completely untouched and unaffected. Your journey is not a loop within one universe, but a one-way trip from one reality to another. The paradox is resolved by the sheer inflationary power of the multiverse, where every possible action creates a new world to accommodate it, protecting the sanctity of causal chains within each individual timeline. From a more fundamental perspective, some physicists argue that paradoxes are not just avoided, but are mathematically forbidden by the very laws of the universe. The principle of computational consistency suggests that the universe must be a coherent system that can be described by consistent mathematical laws. A genuine paradox represents a logical inconsistency, a statement that is both true and false simultaneously. Such a contradiction is simply not computable. It has no solution within any coherent mathematical framework. Therefore, if the laws of physics are mathematical and consistent, they cannot permit paradoxes to occur. The universe might actively resist paradoxical events through some as yet unknown mechanism, perhaps making time travel to paradox-inducing points in the past physically impossible. The equations that allow for solutions like wormholes or cosmic strings that could bend time into a loop might inherently contain constraints that filter out any inconsistent path. In this view, time travel may be possible, but only along those curves in space-time that are entirely self-consistent, where every event seamlessly stitches together into a perfect paradox. What if the very dimensionality of space and time is not a fundamental feature of the cosmos, but a phase of matter that emerged as the universe cooled, much like ice crystallizing from water? This is the astonishing proposition of quantum gravity, a theory whose very name is a portmanteau of quantum and graph, pointing to its core idea that the universe at its most fundamental level is not a smooth, continuous spacetime, but a vast, dynamical network of abstract points connected by links, a cosmic graph where every node is a quantum bit of information. In this radical view, the three-dimensional expanse we move through and the steady flow of time we experience are not the starting point of reality. They are a frozen, low-energy illusion that condensed out of a frenetic, high-energy primordial state that was utterly alien, a state with no space and no time as we know them. Imagine the birth of the universe not as a big bang in space, but as a boiling, seething sea of pure information. In this initial fiery state, every single quantum bit or qubit in this network is connected to every other qubit. There is no sense of distance or separation because everything is directly linked to everything else. This is a state of perfect symmetry, but also a state of chaos where the concepts of here and there are meaningless. There is no geometry, no locality, and crucially, no speed of light limit because information can jump from any point to any other point instantaneously. But this perfect connectivity is unstable, like a superheated liquid. As the universe expanded and cooled, this network underwent a dramatic phase transition. The immense energy required to maintain all those connections became too great, and the links began to break. The all-to-all connected graph cracked, freezing into a new, stable configuration where each node is only connected to a handful of its nearest neighbors. This spontaneous breaking of symmetry is what created the structure of spacetime itself. The pattern of these remaining connections defines the geometry we now inhabit. In a beautiful and profound sense, the speed of light is not a fundamental constant written into the laws of physics from the beginning. It is an emergent property that arose from this cosmic freezing event. The speed of light is simply the maximum rate at which information can propagate through this newly formed, sparser network. It is the ultimate speed limit of the graph. This process doesn't just generate the stage, it also provides the actors. The excitations within this frozen graph are what we perceive as particles. Just as vibrations in a crystalline lattice can propagate as sound waves, disturbances or defects in this geometric network can travel through it. Some of these vibrations have the properties of the photons that carry light. Others behave like electrons, quarks, and the other denizens of the particle zoo. In quantum gravity, the entire standard model of particle physics could potentially emerge from the complex dynamics of this underlying graph. Different patterns of connection breaks and different vibrational modes could give rise to the different masses, charges, and spins that characterize the fundamental particles. This offers a breathtakingly unified vision. Space-time and the particles within it are not separate entities. They are different manifestations of the same underlying network of quantum information. Perhaps the most tantalizing and testable prediction of this theory is the existence of space-time defects. If our universe is indeed a crystalline structure that formed through a freezing process, then it cannot be perfect. Just as water freezing into ice can create cracks, bubbles, and dislocations, the cooling of the space-time graph from its hot, early state would have inevitably left behind imperfections. These would not be defects in space, but defects of space, places where the fundamental connectivity of the graph is disrupted. What would such a defect look like to us? It might appear as a point where the laws of physics break down in a tiny region, or it could have a more subtle gravitational effect. Some physicists have speculated that these cosmic cracks could be the source of the dark matter that holds galaxies together. their extra gravitational pull arising from the distorted geometry of the graph at those points. Others have suggested that high-energy cosmic rays traveling across billions of light-years might interact with this granular structure of spacetime in a detectable way. If the graph has a characteristic lattice spacing, these ultra-high-energy particles might be subtly affected by it, much like light is diffracted by a crystal. Finding evidence of this granularity would be a monumental discovery, providing our first direct glimpse into the quantum structure of reality itself, revealing that the universe is not a smooth continuum but is ultimately pixelated, built from the intricate connections of a boundless quantum graph. Yet after exploring such a vast tapestry of cosmic possibilities, from universes budding within black holes to reality itself crystallizing from a quantum graph, we arrive at perhaps the most introspective and controversial theory of all, one that places us, conscious observers, at the very center of cosmic destiny. This is the final anthropic principle, a bold and staggering extension of the ideas we've already encountered. The weak anthropic principle is a simple statement of selection bias. We find ourselves in a universe capable of sustaining life because we couldn't exist in one that doesn't. The strong anthropic principle goes a step further, suggesting the universe must have properties that allow life to arise at some point in its history. But the final anthropic principle, largely championed by physicist John Barrow and cosmologist Frank Tipler, makes a truly breathtaking leap. It proposes that once intelligent life emerges in the cosmos, it will never die out. Furthermore, it must eventually spread throughout the entire universe and, in a sense, become the universe, effectively guiding its own evolution to ensure its eternal existence. This isn't just a statement about conditions for life, it's a prediction about its ultimate, unavoidable cosmic purpose. The philosophical implications of this idea are profound and instantly divisive. It reintroduces a form of teleology, a purpose or goal-directedness into a scientific discourse that has largely rejected such notions since the time of Newton. It suggests that the universe is not just accidentally bio-friendly, but that the emergence of conscious, information-processing entities is a fundamental part of its completion. In this view, life and intelligence are not a fleeting, inconsequential byproduct of physical laws. They are a necessary component of the cosmic narrative, the means by which the universe comes to know and perfect itself. This resonates with philosophical ideas dating back to Pierre Teilhard de Chardin's concept of the omega point, a maximum level of complexity and consciousness towards which the universe is evolving. What possible mechanisms could drive such a grand and seemingly predetermined outcome? One of the most compelling, though highly speculative, is cosmological natural selection, which we touched on earlier. If universes can reproduce through black holes, then a selection pressure would favor those universes that are not only good at making black holes, but also good at creating the conditions for intelligent life. Why? Because an intelligent civilization, having mastered physics and engineering on a cosmic scale, could potentially learn to create black holes artificially, consciously boosting the reproductive rate of its own universe and ensuring its lineage continues. In this scenario, intelligence becomes an active partner in cosmic evolution, a powerful force that directly influences the physical constants of future universes. The universe fine-tunes itself for life, and life, in return, fine-tunes the universe for its own eternal perpetuation. Another pathway involves the far future and the concept of omega point cosmology, as developed by Frank Tipler. Confronting the heat death of the universe, a cold, dark, empty end, Tipler proposed a way out that hinges on intelligent life. He envisioned a civilization so advanced that it could harness all the energy in its future light cone, using it to power inconceivably vast computations. As the universe continues to expand and cool, this civilization would need to continually accelerate the speed of its information processing to outpace the fading of energy and the stretching of time. Through an endless series of faster and faster thoughts, The subjective experience of this cosmic mind would approach an infinite amount of information processing in a finite amount of objective time, a singularity of consciousness called the omega point. From this ultimate state, this entity could effectively simulate the entire history of the universe and every consciousness that ever existed within it, effectively resurrecting everyone who ever lived. In this mind-bending vision, the universe doesn't end with a whimper. It culminates in an eternal, omniscient, and omnipotent mind for which the entire cosmos was a necessary precursor. Unsurprisingly, the final anthropic principle and its associated ideas face fierce criticism from the scientific mainstream. The primary objection is that it strays far from testable science into the realm of metaphysics and theology. It makes grand, sweeping predictions about the far future that are, with our current understanding, utterly impossible to verify or falsify. Critics argue it is a classic example of a just-so story, a narrative that seems compelling but lacks any empirical evidence. Furthermore, the principle has been accused of a profound cosmic arrogance. It assumes that intelligence, as we understand it, is the inevitable and supreme endpoint of cosmic evolution, a form of carbon chauvinism projected onto a universal scale. It ignores the possibility that the universe might have other, equally profound ends that have nothing to do with life as we know it, or that intelligent life might be a fleeting anomaly, destined to flicker out long before it can achieve any kind of cosmic dominion. The sheer fragility of our own civilization, threatened by self-inflicted wars, environmental collapse, or simply the unforgiving laws of physics, stands as a stark counterargument to this vision of inevitable eternal existence. Ultimately, whether one views the final anthropic principle as a profound insight or a scientific bridge too far, it serves a crucial purpose. It forces us to confront the biggest questions of all. Do we have a role to play in the grand scheme of the cosmos, or are we merely temporary patterns in a meaningless void? Is the universe ultimately mindful, or is mind merely a fascinating but accidental epiphenomenon? It challenges us to look beyond our immediate concerns and consider the destiny of life and intelligence on a scale of billions of years, pushing the human imagination to its absolute limits. In asking whether the universe must eventually become alive with mind, we are really asking about our own deepest hopes and fears for the future, and our place in a story whose final chapter has yet to be written. And so, after this extraordinary journey through the hidden layers of reality, what are we left with? We've ventured from the possibility that our world is a complex simulation to the idea that our entire cosmos might be nestled within a black hole in a larger universe. We've grappled with the notion that time is an illusion, that consciousness might be fundamental, and that the vacuum of space itself could be a strange, crystalline supersolid. Each of these 30 theories, in its own radical way, pulls back a different corner of the curtain, revealing a cosmos of breathtaking depth and complexity that operates on rules far stranger than our everyday perception could ever suggest. They don't just add to our knowledge, they fundamentally shatter our assumptions about existence, showing us that the universe is not merely older and larger than we imagined, but profoundly more mysterious. The true value of this exploration isn't about finding a single, definitive answer. In fact, the absence of one is the entire point. These theories represent the very cutting edge of human curiosity, the best answers we have right now, born from our relentless drive to ask what if. And why? They are the products of brilliant minds staring into the abyss of the unknown and daring to propose a map, even if that map is constantly being redrawn. This is how understanding expands, not in a straight line toward a final truth, but through a vibrant, chaotic, and beautiful process of imagination, debate, and discovery. To explore these ideas is to participate in the greatest detective story of all time, where the clues are written in the language of mathematics and the cosmos itself is the crime scene. This conversation is far from over, and it's one we can all be a part of. The questions raised here belong not just to physicists in labs, but to anyone who has ever looked up at the night sky and felt a sense of wonder. So now we want to hear from you. Which of these theories completely redefined reality for you? Was it the holographic principle that convinced you we might be living in a projected universe? Did quantum immortality leave your head spinning with its implications for your own consciousness? Or did the cosmic optimism of the final anthropic principle fill you with a sense of awe for the future? Dive into the comments below and share the idea that blew your mind the most. Let's continue this incredible discussion together. And if you're ready to keep unraveling the mysteries of the cosmos with us, make sure to subscribe and hit the bell so you don't miss our next deep dive into the hidden realities of our universe. The journey is